What if everything you've ever known, every second, every heartbeat, every sunrise, only exists because time chose to start ticking? What if there was a moment before time itself existed, a universe frozen in nothingness, waiting for its first second to begin? It sounds impossible, right? But there was a time before time. And understanding how time was born might be the key to understanding everything, from why we age to how the universe will end. We measure our whole lives in time. We wake up to alarms, celebrate birthdays, and mourn when time runs out. But we almost never stop to ask, what is time, really? Is it just the ticking of a clock, the movement of the earth, or is it something much deeper? Something that only started when the universe itself was born. In this episode, we're diving into one of the biggest mysteries in science and philosophy, how time began. And we'll look at why time might not be what we think it is, why it might be an illusion that the universe created to make sense of itself. Here's the problem. Everything we understand about time depends on change. A clock moves, the earth spins, the sun rises and sets. Without motion or difference, there's no way to measure time. There's just stillness. So if we go all the way back, before there were clocks, before the earth, before even atoms, how could time have existed? Scientists have spent decades trying to answer this. Philosophers have spent thousands of years arguing about it. And still, we don't have a perfect answer. But we do have clues. Cosmic evidence left behind in the fabric of the universe that tells us when, and maybe even how, time was born. Time is how we understand change. You know something's happening because it's different from what came before. That's it. Time is our way of organizing change into a story. But this raises a weird question. If nothing was changing at all, would time still exist? Imagine a universe where absolutely nothing moves. No atoms, no light, no sound, no thought. If you were somehow inside it, which you couldn't be, but let's pretend, would there be such a thing as before or after? Probably not. Without change, there's no difference between one moment and the next. It's all the same moment, forever frozen. That's what scientists and philosophers mean when they say time began. They mean there was a moment when change itself first became possible. Now, roll back the clock, all the way back to the very start of the universe. About 13.8 billion years ago, the universe was smaller than an atom. Everything that would ever exist was squeezed into one unimaginably dense point. In that instant, there was no before, because before didn't exist yet. When that tiny point expanded, the moment we call the Big Bang, space and time themselves came into existence together. Time didn't start ticking inside the universe. Time is part of the universe. It's like asking, what's north of the North Pole? There's nothing there, because the North Pole is already the edge of north. In the same way, there's nothing before time. The Big Bang wasn't an explosion in space. It was the creation of space and the creation of time. That idea feels strange because our brains aren't built to imagine a reality without time. We live inside it. We experience it every second. Trying to picture a universe without time is like trying to imagine color if you've only ever seen black and white. But scientists can get close using mathematics. Einstein showed us that time and space are connected. They're part of the same fabric he called spacetime. Whenever you move through space, you move through time. That's why astronauts in orbit age a tiny bit slower than people on Earth. Not because of magic, but because space-time bends and stretches depending on gravity and speed. Here's the twist. When the Big Bang happened, that fabric didn't just stretch, it appeared. And with it, the first measurable moment of before and after. Now let's talk about something even stranger. What was happening at the exact moment time began? For that, we have to step into the realm of quantum physics. At the tiniest scales, way smaller than atoms, the universe behaves like a restless sea of energy. Particles blink in and out of existence in fractions of a second. Even empty space isn't truly empty. It's buzzing with quantum fluctuations. So when scientists say the universe came from nothing, they don't mean absolute nothing. They mean it came from a state where the laws of physics as we know them didn't yet apply. In that chaotic quantum foam, time itself may have been undefined. Moments could blur together, happening all at once, or not at all. Then something shifted. A random fluctuation, an imbalance, caused energy to expand outward. That expansion defined direction, and suddenly, the universe had a way to measure then and now. That's when time as we know it began to tick forward. But here's a question that keeps scientists up at night. Why does time flow forward? Why can we remember the past, but not the future? Why does a glass shatter, but never unshatter? The reason might be something called entropy, the tendency of everything to move from order to disorder. Imagine you have a deck of cards neatly arranged by suit. That's low entropy. It's organized. Now shuffle it. The order disappears. That's high entropy. Disorder. The universe behaves the same way. At the beginning, it was in an incredibly low entropy state, compact, smooth, and uniform. As it expanded, things became more chaotic, more mixed. That change from order to disorder gives time its direction. It's not that time flows on its own. It's that the universe keeps changing, and we call that direction the future. So, the arrow of time might not be something built into nature. It could simply be the way we experience the universe's tendency toward chaos. If the universe ever stopped changing, if entropy somehow froze, time would effectively stop too. Now, let's bring this back to us. Because for all the cosmic theories, the weirdest thing about time is how we feel it. To your brain, time isn't a steady rhythm. It's elastic. A boring hour can feel like forever. A joyful day can vanish in a flash. Your perception of time depends on memory, emotion, and attention. When you're afraid or in danger, your brain processes more information per second, making moments feel slower. When you're relaxed or distracted, time speeds up. It's a reminder that time, in a very real sense, is something your mind creates as much as it experiences. And that raises a deep question. If we could somehow see the universe from the outside, without memory, without perception, would time even exist? Einstein once said that for people who understand relativity, the distinction between past, present, and future is only an illusion. All moments, from the birth of the universe to your next breath, coexist in the same four-dimensional fabric. We experience them in sequence, but to the universe, every moment simply is. So maybe time doesn't pass at all. Maybe we move through it, like pages in a book. The story is already written. We just experience it one chapter at a time. Now picture this. The very first second after the Big Bang. Not metaphorically, literally, the first second of existence. In that instant, the universe went from a tiny point to a vast expanding field. Temperatures were beyond imagination, trillions of degrees. Quarks and electrons were born in a storm of energy. Space itself was stretching faster than the speed of light. If you could somehow witness that moment, you wouldn't see an explosion. You'd see creation itself. space and time unfolding together, painting the cosmic canvas for everything that would follow. That was the birth of motion, the start of cause and effect, the first heartbeat of time, and all of it. Galaxies, stars, planets, you, was contained in that first instant. The first second was enough to set the laws of physics, the strength of gravity, and the passage of time itself. In that single heartbeat, the universe learned to count, and it has been counting ever since. So, what is time? Maybe it's not something we move through, but something that moves through us. Maybe time is the universe's way of making sure everything doesn't happen at once. From the first fraction of a second to the ticking of your wristwatch, it's all part of the same story. A story about change, about growth, about the unstoppable unfolding of reality. And even though we can measure time, divide it, and try to control it, deep down, we're still living inside that first moment, the universe's original breath, expanding ever outward. Every second you experience is a continuation of that first spark. Time didn't just begin at the Big Bang. It is the Big Bang, stretched out and slowed down so we can live inside it. In the beginning, before any clock could tick or any second could pass, there was a silence beyond silence, a void without before or after, a stillness without change. This was the cosmos in a timeless state, an existence with no yesterday and no tomorrow. In this primordial hush, not even a single moment could be counted, for the very concept of time had yet to awaken. It is almost impossible to imagine such a condition. We are beings bound to time. Every heartbeat, every sunrise, every thought takes place in time's steady current. All our memories and hopes line up in a sequence of then, now, and next. To picture a realm where time does not exist is to imagine reality paused on a frame that never changes. In that pause, there is no change, no aging, no duration, only an eternal now that somehow encompasses all possibilities. Yet countless myths and legends begin with just such a void and stillness. Ancient storytellers spoke of chaos or nothingness before creation. They told of darkness upon the face of the deep, of silent emptiness before the first word or the first light. In a way, the scientific story of the universe begins similarly, with a profound nothingness. Before time began, the universe to be was a singular state, perfectly uniform, containing all the mass and energy that would ever exist, tightly bound in a fraction of space smaller than a mote of dust. Even describing it in such terms is misleading, because space itself had not yet unfolded. There was no distance between points, no outside into which to place that primordial seed of everything. Modern physics teaches that space and time are interwoven, two strands of a single fabric. In that prelude to existence, that fabric was not yet woven. All of reality was simply one all-encompassing essence, curled up on itself. And in this state before space and time, there was no past or future, only a physics-defying equilibrium, like a held breath before a plunge. What does it mean? A cosmos without time. It means nothing could happen, for happening requires time. No births, no deaths, no movement or change, only an unchanging being. A million events might be possible in theory, but none could leave any mark, because there was no time in which anything could unfold. This timeless universe was neither dead nor alive. It simply was, a silent, immutable isness beyond the flow of seconds or the tick of any clock. And yet, Hidden in that endless stillness was the potential for everything. If one could somehow peer into this state of timelessness, they might sense a tremendous tension, like a wound spring waiting to release its energy. All the forces of nature that we now know, gravity, electromagnetism, the nuclear forces, were unified in that singular essence. The conditions were extreme beyond comprehension, density and temperature so intense that the familiar fabric of reality was strained to its limits. Space and time, insofar as they existed in that seed, could not behave in any ordinary way. At this ultimate moment of balance, something inevitable was about to occur. The silence before creation was pregnant with possibility. The cosmos could not remain in this featureless perfection indefinitely. The very energy of that tiny seed yearned to expand, to express itself. It was as if the entire cosmos was holding its breath, poised at the threshold of an immense release. Just as a quiet inhale must at some point turn into an exhale, the universe was primed for a tremendous exhalation of creation. Then, in a moment beyond imagining, the stillness broke. The timeless realm yielded, and time itself was born. The first moment of now arrived, and nothing would ever be the same. A new cosmic story was about to unfold. Time has begun. In a blinding instant of creation, the newborn universe flares into existence. What was an infinite stillness is now an ocean of energy and light, unfurling in all directions. The first moment of time is indescribably brief, and yet filled with unfathomable brilliance, as the cosmos takes its first breath. For the first time, there is light and motion. Where once there was nothing, now there is the fire of creation itself. In that first fraction of a second, the universe rushes outward, expanding at a rate beyond anything we can compare. Space itself is stretching, carrying galaxies to be apart even before they exist. Distances that were zero grow vast in a mere heartbeat of time. In fact, the universe doubled in size again and again in that tiny instant, an exponential surge. In the span of a sliver of a second, the universe that was nowhere is suddenly everywhere, its size multiplying unimaginably. The infant cosmos is incredibly hot, so hot that no distinct particles can yet survive. Everything is a blur of pure energy, a glowing plasma where matter and light are the same substance. It is a blinding, seething fog of radiation, filling all of space. Time here is measured not in seconds or even microseconds, but in the furious interactions of primordial energy. And the fundamental forces of nature themselves are only just beginning to emerge from their unified state as the universe cools, ever so slightly, with expansion. In those fleeting instants after time's birth, nature's forces begin to step apart, like dancers moving to different rhythms. Gravity is the first to break free, establishing itself as an independent force, weak compared to the others, but pervasive, giving shape to space-time. Almost immediately afterward, another critical change unfolds. The force that will one day bind atomic nuclei, the strong nuclear force, separates from the unified field of forces. This moment unleashes an enormous surge of energy into the young universe. Space inflates with unbelievable speed, a dramatic swelling that happens faster than any explosion, flinging the fabric of the cosmos outward. In the next moments, as the universe continues to expand and cool, another symmetry breaks. The electro-weak force, which had unified the forces of electromagnetism and the weak nuclear interaction, splits into two separate pieces. From now on, the force of light and electricity, electromagnetism, and the weak nuclear force will operate independently. Within mere fractions of a second, all four fundamental forces of nature have assumed their separate identities. each ready to play its part in shaping the unfolding cosmos. Within less than a heartbeat of creation, the blueprint for everything is imprinted in the expanding fireball. Tiny fluctuations, random little variations in that seething energy, are stretched out across the universe. They were quantum whispers on the microscopic scale, now blown up to enormous proportions by the rush of expansion. These minute irregularities are so small as to seem insignificant, just one part in 100,000 of difference from place to place. Yet they are the seeds of galaxies and clusters and all the structure to come. Though the young universe is almost perfectly smooth, those faint imprints mean some regions are ever so slightly denser than others. In time, gravity will amplify those differences, drawing matter into the dense spots. Carried by the rush of expansion, the tiny initial pattern is set, a subtle patchwork in the otherwise uniform glow, which will eventually guide the formation of stars and galaxies billions of years later. As the first second of existence unfolds, the extreme intensity of those initial moments begins to ease just a little. The flood of energy starts cooling enough to conjure matter from pure light. Pairs of particles and antiparticles appear out of the radiant heat, tiny flickers of substance popping into being, like electrons with their mirror opposites, positrons, or quarks with their antiquarks. They meet and annihilate in brilliant flashes, matter turning right back into light. For the most part, creation and destruction are balanced, like perfect twins cancelling each other out. But by some small cosmic bias, perhaps only one particle in a billion survives without a partner to destroy it. It is as if a vast lottery is being played over and over, and each time only a few solitary winners emerge. Those few lonely survivors, mere traces in that vast fire, will eventually gather to become all the atoms of the galaxies, stars, and worlds. Before even a single second has passed, the basic ingredients of the universe are in place. The fabric of space-time is expanding rapidly, carrying with it the glowing broth of particles and radiation. The universe is still impossibly hot and dense by any normal standard, billions upon billions of degrees, but it is cooling and thinning with every passing moment. Tiny particles are starting to slow their frenetic dance as space opens up. Time marches on, even if no conscious eye is yet there to witness it, and with each fraction of a second, new possibilities emerge from the primal chaos. To us, a second is hardly noticeable, a brief snap of the fingers. Yet in that first second of cosmic time, more change and drama unfolded than will happen in billions of years. Entire eras of physics flashed by in instants. Forces split and took their roles, space ballooned, matter formed and was unmade in a dance of light. The arrow of time had firmly taken hold, moving in one irreversible direction, outward and forward, away from that incandescent beginning. And still, there is a deep mystery in those earliest moments. The closer we push toward time's 0 point, down to trillionths of a second, the scale of the Planck time, the less our conventional physics can tell us. The first instants of time were governed by quantum uncertainty, where the usual rules of cause and effect grew hazy. According to what we know, events at that scale defy common sense. Reality behaves more like shifting probabilities than solid facts. To truly witness the birth of time, we must delve into a realm where space and time themselves were intertwined in a quantum haze. It is a realm unlike anything in our everyday experience, a realm we now turn to explore. Let us pause on the threshold of the very first moment. To explore the birth of time more deeply, we must shrink our perspective down to the smallest scale imaginable. We are now peering at the universe when it was less than a trillionth of a second old, a time so early that our usual ideas of space and time cease to make sense. At this incomprehensible scale, space itself is a froth of quantum fluctuations, and time is not yet a steady beat, but a trembling uncertainty. On this quantum stage, the ordinary rules of reality blur into something strange. Space and time, which we usually think of as distinct, are inseparably intertwined here. Imagine a fabric so tightly woven that you cannot tell one thread from the other. Such is space-time at the outset, a single entity quivering with potential. Past and future have no clear meaning. An after might happen before, without contradiction, in the churn of creation's lowest depths. Cause and effect, the sequence of events we take for granted, become ambiguous when viewed up close in this arena. In this realm, energy flits in and out of existence in tiny bursts. Virtual particles, brief sparkles of being, appear and vanish incessantly, as if the universe is testing out countless miniature possibilities. The uncertainty principle reigns supreme. If we try to pin down exactly when or where something happens, nature responds with a blur. If you attempt to measure a precise moment, the energy involved swells wildly, erasing any clarity. Time itself in this quantum soup behaves less like an arrow and more like a cloud, diffuse, scattered, and unpredictable. Physicists call this the Planck era, the domain where our classical understanding utterly breaks down. We have no direct observations of this epoch. It hides behind a veil that our instruments and equations cannot yet penetrate. Some theories even suggest that at this ultimate beginning, time as we know it did not exist at all. The universe might have been in a timeless state, everything, everywhere, all at once, until a kind of transition sparked the flow of time. It is a moment so alien that words fail. Before and after only emerge once the chaos settles and time gains its footing. Picture space-time as a seething cauldron of foam. Tiny bubbles, tiny universes perhaps, form and dissolve in the blink of an eye, far too quickly for any clock to measure. The geometry of space twists and flickers erratically. One instant, a minuscule loop of space might pop into being. An instant later, it collapses back into nothingness. Time could speed up in one microscopic patch and slow down in another. It might even twist into a closed loop for a fleeting heartbeat before unraveling again. This was a cosmic soup of quantum possibilities, a true wilderness at the edge of time. Within this froth, space and time were truly entangled. One could not be defined without the other. A change in one meant a change in the other. They were two faces of the same fundamental reality, shaking out the rules that would eventually govern the new universe. To speak of when something happened is almost meaningless at this scale. All we can say is that out of this fluctuating backdrop, a path for time began to emerge as the universe grew just a bit larger and a bit older. Slowly, as the universe expanded during those first incredibly tiny fractions of a second, the chaos began to ease. The energy dropped just enough for space-time to start becoming a little more stable and smooth. The wild quantum waves that once distorted reality averaged out, like choppy water calming as a pond grows wider. In that calming, time found a direction. It began to flow more uniformly, paving the way for the next stages of cosmic evolution. Thus, from the quantum haze, the familiar flow of time was born. The universe left behind the jittery uncertainty of its first moment and entered a new phase of expansion and cooling, a realm we can begin to describe with ordinary physics. Now, with space and time no longer in total turmoil, the stage was set for an event of spectacular proportions. This would be the great inflation that would shape the young universe's fate. Almost as soon as it began, the universe was swept up in an extraordinary growth spurt. In an infinitesimal fraction of a second, the cosmos underwent what we call inflation, an explosive expansion of space itself. This epoch was unimaginably brief, yet during it, the universe swelled exponentially, doubling in size over and over at a furious pace. A region of space, no bigger than a subatomic particle, ballooned to macroscopic proportions in a heartbeat of time. It was as if the universe went from the size of an atom to the size of a galaxy in one cosmic blink. During this phenomenal expansion, space stretched so swiftly that it outpaced even the speed of light, though without breaking any cosmic speed limit, since it was space itself expanding. All the tiny irregularities and curves in space were smoothed out almost completely. Imagine a crumpled sheet of paper suddenly pulled taut. All the wrinkles flatten. Inflation ironed the young universe in much the same way. The result was that the cosmos became extremely uniform from one end to the other. Places that would forever be far apart were, before inflation, close together and able to share the same conditions. When inflation blew them apart, they still retained those matching properties. The temperature and density of the early universe ended up almost exactly the same everywhere. To any observer inside, space would appear remarkably flat and even, no matter where they looked. Yet inflation did more than just smooth things out. It also preserved a tiny imprint of randomness. Those minute quantum fluctuations, the little differences in density we spoke of earlier, were stretched across the sky. Inflation took subatomic whispers and amplified them to cosmic volume. In the aftermath of inflation, the universe was nearly featureless, but not perfectly so. There were faint imprints, slightly denser patches, and slightly thinner ones, left behind by that rapid expansion. These slight variations were only one part in 100,000, but they were crucial. They were the seeds from which galaxies and clusters would eventually grow. Inflation, in effect, set the stage for structure by scattering tiny seeds of imbalance throughout an otherwise smooth expanse. The inflationary epoch was incredibly short-lived, ending almost as suddenly as it began. After an almost inconceivably short moment, the tremendous expansion slowed dramatically. All the energy that had driven space to expand so furiously had to go somewhere, and it poured into the fabric of the universe, superheating the young cosmos. This moment is often called reheating, when the decay of the inflationary field filled space with a flood of particles and radiation. In an instant, what had been cold, empty vacuum during inflation became a fireball of hot matter. The universe, still less than a second old, was now a searing, dense plasma once again, as if the tremendous energy of inflation had ignited a cosmic furnace. With inflation over, the universe's expansion settled into a calmer, more steady pace. The extreme growth spurt gave way to the more gradual expansion described by the traditional Big Bang evolution. From this point on, the universe's large-scale behavior was less exotic and more comprehensible. One could say that, at the end of inflation, the universe's clock started ticking in earnest. The incredible chaos of the very beginning had subsided enough that time could be marked by the changing conditions of the cosmos. The temperature of the primordial fireball began to fall as the universe expanded, and this cooling acted like a natural cosmic clock. With each tiny decrease in the blistering temperature, a moment of time had passed, like the ticking of a second hand. Indeed, the cooling of the post-inflation universe serves as a kind of timetable for the events that followed. Every drop in temperature and density signaled that the universe had reached a new milestone. In principle, if we were to measure the heat of the universe at that time, we could tell how many fractions of a second had elapsed since the Big Bang. The concept of time now had practical meaning. A second in one part of the cosmos was the same as a second elsewhere, because inflation had made everything so uniform and connected. In the wake of inflation, the universe was a vast, hot, glowing fog of particles and light, but a fog that was uniformly spread and already carrying the slight imprints of future galaxies. Time flowed forward, and as it did, the features of the universe slowly began to emerge from the glare. What had been an almost featureless explosion would, over time, condense into the rich structures we know. The chaos had been tamed just enough to allow order to begin forming. The era of inflation had set the initial conditions, and now the universe moved into the next chapter of its story. The furious expansion was behind it, but the aftermath would be just as important. As the seconds ticked by on this newborn cosmic clock, the hot plasma left by inflation continued to cool. In that cooling, fundamental changes were imminent. Particles would join to form the first atomic nuclei. Light would eventually break free to illuminate the darkness, and the smooth glow of creation would fragment into stars and galaxies. The flow of time, started at the Big Bang and turbocharged by inflation, was now carrying the universe from its initial chaos toward an ever more structured existence. The stage was set for the transformation from the fireball of creation into the richly textured cosmos we inhabit, a transformation that was about to begin. In the fiery aftermath of inflation, the young universe was a chaotic sea of particles and radiation. What had been an almost uniform glow still churned with incredible heat and density. In the first microseconds, free quarks, the fundamental building blocks of matter, found one another and clumped into protons and neutrons. The blistering quark soup of moments before gave way to a new kind of order, the first stable subatomic particles. The universe, though still chaotic and hot, was beginning to settle into recognizable constituents. As the universe continued to expand and cool, it reached a critical milestone just a few minutes after the Big Bang. Temperatures dropped enough for protons and neutrons to start sticking together. In those first minutes, nuclear fusion occurred on a cosmic scale. Proton met neutron to form the first atomic nuclei. The simplest element, hydrogen, emerged in abundance, and a small fraction of those protons fused with neutrons to create helium nuclei. In roughly the time it takes to cook a pot of soup, the basic recipe of the cosmos was established. About 3/4 hydrogen and 1/4 helium by mass, with trace amounts of lithium. The first elements were born out of the fire, an early sign of order emerging from chaos. Still, the universe was nothing like the clear cosmos we see today. For thousands upon thousands of years after those first nuclei formed, matter and light were locked together in a hot, opaque plasma. Electrons, the lightweight counterparts to protons, were roaming free, too energetic to settle down. Any time an electron tried to bind to a nucleus, a high-energy photon would smash it away. Space was filled with a brilliant glow, but it was a trapped glow, photons scattering off free electrons in every direction. The universe was like an extremely dense fog of light and charged particles. To an imaginary observer, then, everything would appear as a bright, featureless haze. No star or structure could yet be seen, because light could not travel unimpeded. This was the young universe in its opaque childhood, brilliant but obscure, a glaring chaos of light and matter. After roughly 380,000 years of expansion and cooling, a transformative change occurred. The temperature dropped to about 3,000 degrees, cool enough for electrons to finally settle into orbit around nuclei. Suddenly, electrons latched onto hydrogen and helium nuclei and stayed there, turning plasma into neutral atoms. It was as though a cosmic fog lifted. For the first time, light could travel freely without being constantly bounced around by free electrons. Up to this moment, the universe had been opaque. Now it became transparent. Photons that had been trapped in the primordial glow could now stream across space unhindered. The whole universe released a burst of light, a flash that marked the end of the cosmic darkness of the plasma era. That light is still detectable today as a faint afterglow permeating the sky, the cosmic microwave background. It is a gentle whisper of the time when the first atoms formed and the cosmos opened its eyes. With the formation of atoms, the universe had taken a major step toward order. But it was a dark order. The brilliant primordial light gradually faded into the infrared and radio spectrum as the universe expanded, leaving no new sources of visible light. What followed is often called the cosmic dark ages. The universe now was transparent and filled with matter, but without stars or galaxies yet shining. Vast clouds of hydrogen and helium gas drifted through the darkness, carrying within them the tiny density variations left by inflation. The stage was set in this quiet darkness for gravity to begin its work on those gas clouds. Slowly, inexorably, gravity drew the slightly denser regions of gas into even tighter clumps. Over tens of millions of years, the faint seeds of structure grew. Gas cooled and collected in ever-thickening patches, and within those, smaller knots began to form. Imagine a night sky with no stars, only immense, cold clouds shrinking and heating invisibly from within. In these contracting pockets, the first real sparks of change were imminent. As clump upon clump of gas gathered, the pressure and temperature at their cores climbed. There comes a point when a collapsing gas cloud becomes so hot and dense that hydrogen atoms begin to fuse together. After perhaps 100 million years or more of cosmic darkness, that point was reached. Somewhere in the vast darkness, the first star ignited, and then another, and another. The cosmos was no longer lightless. These first stars were unlike any that exist today. They were born of pure hydrogen and helium, likely much more massive and luminous than modern stars. They burned a brilliant blue-white, enormous beacons lighting up pockets of the young universe. Their light poured into the darkness, illuminating the gas around them and ending the cosmic dark ages. With the birth of the first stars, the universe experienced its first dawn, a cosmic dawn. The appearance of the first starlight was a turning point from chaos toward order. Those stars gathered in groups, forming the first primitive galaxies, little clusters of stars that gravity held together. In time, these would merge and form larger galaxies. But even at this early stage, the architecture of the cosmos was taking shape. The once uniform universe was now dotted with points of light. The raw, formless cloud of gas had given rise to a structured cosmos filled with stars arranged in galaxies and clusters. What had begun as a featureless fireball had now become a vast expanse of wonders. The young universe, still in its infancy by cosmic standards, was no longer a homogeneous sea of particles. It had become a complex tapestry of energy and matter. Glowing stars, embryonic galaxies, and great stretches of space between filled with the faint glow of the first fires. The transformation from chaos to order was well underway. Time, the ever-present conductor, had guided the universe through these transitions. In a few 100 million years, the universe went from opaque chaos to a structured, starlit cosmos. And this was only the beginning of the grand story. The cosmic clock would continue to tick, and with each passing eon, new layers of complexity would emerge. From the first atoms to the first stars, and eventually to planets and life, The journey of the universe was just starting. The once lightless expanse was now alive with starlight, and the path of time would lead onward, ever unfolding new chapters of creation. In the aftermath of the universe's blazing birth, time carries us forward into a sea of brilliant, primordial fire. Space itself is aglow with energy and light, stretched thin by a furious expansion, yet still unimaginably hot and dense. In these first moments, matter and light are entwined in a radiant fog, an opaque brilliance flooding every corner of existence. The universe is young and chaotic, but each passing heartbeat of time gently cools the inferno, guiding the cosmos from pure fire toward a future of form and structure. It is a scene of pure brilliance and fury, a newborn cosmos glowing as if it were an all-encompassing star. In those early seconds, temperatures soar to billions of degrees, so intense that atoms cannot yet exist. Particles flicker in and out of the incandescent mix. Electrons, protons, and other exotic specks jostling amid the blinding glow. At these energies, matter and antimatter are created as twin pairs, only to collide and vanish in bursts of pure energy. By a subtle cosmic twist, a slight excess of matter endures this mutual annihilation, seeding the young universe with the material that will eventually form stars and galaxies. As space expands, that seething soup begins to settle ever so slightly. Protons and neutrons start to bind together, forging the first atomic nuclei in brief, miraculous unions. Each collision and combination marks the birth of a new element: hydrogen, helium, and tiny traces of lithium, forming against the odds in a universe still too hot to hold them for long. In a matter of only minutes, this newborn universe has created much of the hydrogen and helium that will populate the cosmos for billions of years to come. By the time this brief alchemy is done, roughly 1/4 of the universe's ordinary matter has transformed into helium nuclei, while the rest remains mostly hydrogen with only the faintest whispers of lithium. But as swiftly as it began, this first fire of creation cools enough that it can forge no more. The cosmic crucible falls silent, leaving behind a vast ocean of searing plasma filled with free-roaming electrons and glowing atomic nuclei. The temperature remains far too high for those nuclei to capture electrons as atoms. Light ricochets off the loose electrons in every direction, trapped in a brilliant haze, as if the universe were a star turned inside out. To an imaginary traveller in this infant cosmos, there would be no distinct objects to see, no stars or planets, no galaxies, not even a hint of darkness between. They would be immersed in a boundless expanse of light and energy, as if floating inside the core of an endless star. All around them, every direction offers the same searing brilliance, uniform and overwhelming to any senses. Space has not yet known darkness or shadow. It is filled everywhere by the burning radiance of creation's first light. Time has not yet brought night or form, only an endless, blinding present. For a long while, the universe remains in this luminous, opaque state. Thousands, then millions of years pass in a slow cosmic dawn that has yet to reveal any stars or galaxies. Time flows onward, and with each passing epoch, the plasma cools a little more, the light within it stretching to longer, gentler wavelengths. The brilliant white-hot glow softens to a warm ember as the expansion continues. After hundreds of thousands of years, the once blazing cosmos has cooled to a few thousand degrees. In this steady cooling from chaos toward order, the arrow of time finds its direction, a one-way march from the universe's fiery infancy into its unfolding future. At last, a quiet threshold is reached. The fog is ready to lift, and something fundamental is about to change. Hundreds of thousands of years after the Big Bang, the cosmos finally cools to a critical point. By now, the temperature has fallen to roughly a few thousand degrees, cool enough for a quiet revolution to occur. Free electrons, which for ages wandered unattached, begin to settle down and bind to atomic nuclei. For the first time, complete atoms of hydrogen and helium form out of the primordial fire. In an instant, the blinding fog of charged particles that filled space starts to clear. With electrons locked into atoms, they no longer block the path of light. The universe, once opaque like a cloud of glowing plasma, suddenly becomes transparent. In that moment, light bursts forth across the cosmos. Photons that had been trapped for eons now stream freely in all directions. As each electron finds its home in an atom, it releases a tiny packet of energy. Collectively, these millions upon millions of little emissions create a gentle glow permeating space. The young universe is briefly awash in a warm, diffuse radiance, like the embers of a cosmic dawn. This glow is the very first light able to traverse the universe unimpeded, carrying with it the imprint of everything that came before. Eons later, this primordial glow can still be detected as a faint whisper in the darkness. The cosmic microwave background, a remnant of that early time still traveling the skies. For instance, one can imagine a single particle of light, a photon, born in that first dawn of transparency. For hundreds of thousands of years, it was forced to zigzag, bouncing between electrons in the dense fog, never getting very far. But once the fog cleared, that photon found open space and set off on an incredible journey. It has been traveling ever since, crossing billions upon billions of miles through the expanding universe. Over the eons, its wavelength stretched and its energy gentled, transforming from a fiery ray of light into a cold microwave whisper. In modern times, that ancient photon might end its long voyage by nudging an antenna on a satellite, finally delivering its message from the epoch when the cosmos first became transparent. For a while, the entire universe is bathed in this radiance. If one were present then, they would see a soft, uniform glow filling the heavens from every side. A sky lit not by stars, but by the universe's own newborn light. Yet as the cosmos continues to expand, this glow begins to fade and cool. The once blazing light stretches into longer wavelengths. What was orange and brilliant dims to red, then slips beyond the visible spectrum into the infrared and radio. The fire of creation, having momentarily illuminated all of space, ebbs into a gentle afterglow. Before long, to human eyes, the universe becomes dark once again. Thus begins the long cosmic night, known as the Dark Ages. The universe is transparent now, but there are still no stars to shine in the void. All around is vast darkness, punctuated only by the faint background glow of the cooling radiation. Imagine drifting through this epoch. You would find yourself in a silent, black expanse. No galaxies or suns light your way. Only a feeble warmth left over from the universe's fiery birth, now stretched thin and cold. The gas of the cosmos, mostly hydrogen and helium, lies invisible all around you, holding the potential for future stars. The cosmos seems to hold its breath in this deep night, awaiting the first spark of a new dawn. Even in this darkness, quiet changes are underway. The newfound atoms occasionally meet and link in simple unions, marking the dawn of chemistry. Helium joins with hydrogen, to form a rare molecule called helium hydride, the very first molecule in the universe. These molecules, though few, help the gas cool further by radiating away energy. In time, hydrogen atoms pair up into molecules of hydrogen gas, another step in chilling the cosmic air. Bit by bit, the cooling and gathering of gas continue, aided by these tiny molecular actors. All the while, another force has been patiently at work: gravity. In the absence of starlight, gravity moves silently through the dark, tugging ever so gently on the densest regions of gas. Invisible halos of dark matter, mysterious mass that emits no light, are also drawing the gas inward, providing an unseen scaffold for these developing structures. Over millions of years, small clumps of matter draw in more and more material, growing denser and heavier. These are the seeds of future stars and galaxies, assembling unnoticed in the blackness. The cosmic clockwork is quietly winding up, preparing to spark the next dawn. Soon, under gravity's influence, the deep darkness will be pierced by new light. The first stars are waiting to be born. In the starless darkness of the young universe, gravity continues its silent work, drawing matter together. But gravity's influence is not limited to shaping the cosmic landscape. It also reaches into the flow of time itself. According to Einstein's profound insight, space and time are interwoven, and mass can bend this unified fabric. The presence of matter doesn't just tug on other matter, it warps space and slows the passage of time. Imagine space-time as a flexible sheet, and planets, or stars, as heavy weights pressing down on it. Near a massive object, the sheet of space-time dips into a well, and time in that gravity well runs more slowly compared to regions with weaker gravity. A clock placed deep in a strong gravitational field ticks more leisurely than one far out in open space. The stronger the gravity, the more pronounced this effect becomes. Time itself stretches out in the presence of mass. For centuries, time was assumed to be absolute and unchanging. Only in the early 20th century did that view shift, when Albert Einstein proposed his revolutionary ideas of relativity. He suggested that time could stretch and skew under the influence of gravity, a prediction that sounded like fantasy at first. Over the years, experiments with precise clocks and careful astronomical observations confirmed Einstein's theory. Gravity truly does affect the flow of time, just as he envisioned, and what was once a strange idea is now proven reality. For most of the universe, this warping of time is extremely subtle, yet it can be measured with sensitive instruments. High above Earth, where the pull of gravity is weaker, clocks tick slightly faster than those at sea level. Engineers must correct for this tiny difference in the clocks aboard GPS satellites, proving that these predictions of relativity are not just abstract theory. On a far more extreme scale, near the edge of a black hole, time's flow slows dramatically. As seen from a distance, a clock near a black hole's dark horizon would appear almost frozen, its seconds stretching unimaginably long. If we could observe the cosmos from two different vantage points, one deep in a gravitational well and one far out in emptier space, we would notice their clocks disagree on the timing of events. A process that lasts a certain interval far from gravity might last slightly longer, close to a massive object. In the early eons, when matter was spread nearly uniformly, such differences were vanishingly small. Time marched almost in unison everywhere. But as massive stars and galaxies formed, little pockets of slower time appeared around them, tiny local variations in the great cosmic clock. Gravity thus plays a double role in the universe. It sculpts the structures of galaxies and stars, and it subtly tunes the flow of time. We seldom notice these effects in daily life, yet they are real. an ever-present reminder that time is not rigid or universal, but part of the living physics of the cosmos. This realization adds depth to our understanding of time's birth and evolution. Even time has a history, shaped in part by gravity's enduring pull. In the cosmic perspective, time is woven into the same fabric that gravity shapes, making the passage of seconds as dynamic as the dance of galaxies. In those silent centuries before the first stars, gravity had already begun to weave its effects on both space and time. As gas clouds contracted under gravity's guidance, they set the stage for new stars. In doing so, they also created tiny wrinkles in time's flow around them, infinitesimal slowdowns near the dense centers of collapse. Now, as those clouds reach critical density, they are poised to burst into starlight. Gravity's long labor is about to reveal its reward. In the next moment of cosmic history, darkness will give way to light as the first stars are born, marking a new chapter in the story of time. At last, roughly 200 million years after the Big Bang, the long night of the cosmos is broken. Deep within a particularly dense cloud of primordial gas, pressure and heat build relentlessly under gravity's squeeze. Finally, a profound transformation occurs. Hydrogen atoms begin to fuse into helium in the cloud's core, releasing a torrent of energy. A brilliant new light blazes out of the darkness. The first star has been born. After ages of blackness, the universe witnesses its first true sunrise, a single point of starlight shining defiantly in the cosmic void. This first star is a solitary beacon in a vast, dark sea. Its radiance illuminates the surrounding nebula of gas, casting a faint glow into the cosmic night. For the first time since the Big Bang's initial afterglow, there is a new source of light piercing the emptiness. One can imagine the scene, where once there was only cold, silent nothingness. Now a fierce, blue-white star burns, a beacon heralding the end of the cosmic dark ages. It is the cosmos's first candle, and by its light, the universe is no longer utterly lightless. If we could watch the sky during this cosmic dawn, we would witness an awe-inspiring transformation. At the beginning of the era, the heavens would be almost completely black, save for a dim haze left from the Big Bang. Then, gradually, tiny sparks would appear. First one star, then another, and another, as newborn suns flicker into existence across the darkness. Over millions of years, these pinpricks of light multiply into a multitude of stars. The once empty firmament becomes a glittering tapestry as the universe slowly fills with the fires of countless young stars. The cosmic night, so long unbroken, is now studded with starlight as the first galaxies assemble their shining members. It is as if the universe, after a long darkness, has opened innumerable bright eyes. These pioneer stars are unlike most of the stars we know today. Formed from pure hydrogen and helium, without heavier elements to cool the gas, they grow to be extremely massive. Many of the first stars may have been tens or even hundreds of times the mass of our Sun. Such giants burn at tremendously high temperatures, shining millions of times brighter than the Sun with a searing bluish-white light. They live fast and die young. Their great mass causes them to consume their nuclear fuel at a furious rate, so their lifespans are only a few million years, a mere eye blink on cosmic timescales. The light from these first stars begins to transform the universe around them. Intense, ultraviolet rays pour out, flooding into the cold hydrogen gas that fills space, in the immediate vicinity of a new star. That starlight strips electrons off hydrogen atoms once more, turning the gas back into glowing plasma. Each first star, thus creates an expanding bubble of ionized gas in the darkness around it. As more stars form in the neighborhood, these bubbles of light grow larger and start to merge. Gradually, the darkness between galaxies is pushed back by the brilliance of young stars reionizing the universe's hydrogen. In time, this process, essentially turning the lights back on across the cosmos, spreads throughout space, marking the definitive end of the cosmic dark ages. A once lightless universe is now filled with radiance in all directions. Yet the first stars are destined for spectacular ends. Having burned so brightly and briefly, they soon exhaust their fuel. In rapid succession, many of these primordial giants die in cataclysmic explosions, supernovae of almost unimaginable power. One moment, a star that outshone whole galaxies. The next, it blows itself apart in a brilliant eruption that can outshine an entire young galaxy. These explosions send shockwaves rolling through the surrounding gas and hurl newly forged elements into space. In their final fiery moments, the first stars seed the cosmos with heavier elements, the carbon, oxygen, and iron that will one day be essential for planets and life. Meanwhile, the very largest of these first stars may have collapsed directly into black holes without any explosion, planting the seeds of those dark giants that would later grow at the centers of new galaxies. The debris from those first supernovae enriches the once pristine cosmic gas with traces of elements beyond helium. When the next generations of stars begin to form, they inherit this enriched material. The presence of heavier elements allows gas clouds to cool more efficiently and fragment into smaller clumps, leading to the birth of stars that are smaller and longer lived than the towering first generation. In this way, the first stars pave the way for a more complex universe. They establish the chemical foundation for galaxies, planets, and living beings to emerge in later epochs. Though short-lived, their influence is enduring. Every atom of carbon in our bodies, every speck of calcium in our bones, was forged in the furnace of some ancient star, and the very first stars began that cosmic alchemy. As the millennia pass, more stars spring to life out of collapsing gas clouds. The first star is soon joined by others, forming clusters of young suns. Gravity draws these stellar clusters together. Over several 100 million years, the first stars and clusters collect into the first small galaxies. The dark early universe gradually fills with a faint web of starlight as these nascent galaxies twinkle into existence. What was once a featureless expanse now becomes structured. Clumps of stars bound together into the earliest galaxies, blazing as new beacons across the young cosmos. The universe's childhood is ending, giving way to a grand adolescence filled with the light of billions of stars. This era, often called the cosmic dawn, is a turning point in the story of time. The universe has transitioned from darkness to light, and the glow of those first stars marks the ages that have since passed. The photons released so long ago travel through the expanding universe, their color slowly shifting toward red as space stretches. But they are never completely lost. Today, with powerful telescopes, we capture faint traces of that early starlight. When we observe a distant galaxy that formed in this epoch, we are looking deep into the past, seeing it as it was nearly 13 billion years ago. These ancient lights act as time capsules, allowing us to measure the universe's age and remember how far the cosmic clock has ticked since the first stars flickered on. In our own Milky Way galaxy, astronomers have found stars that are almost as old as the universe itself. These venerable stars, living fossils from the dawn of time, contain only tiny amounts of heavy elements, a chemical signature of their primordial origin when the cosmos was still mostly hydrogen and helium. By studying such pristine stars, scientists can infer how many generations of star birth and death have occurred, and estimate the time that has passed. The ages of these old stars, calculated from their compositions and slow-burning fuel, serve as a cross-check on the age of the universe itself. These rare elders are living links to a nearly forgotten epoch. Their faint glow, a direct echo of the universe's youth. They remind us that the first stars truly were cosmic beacons, marking the beginning of the great journey through time, and that their light still guides us in understanding the ages that followed. In the evolving galaxies of the young universe, a pattern of stellar life emerges. Stars are continually being born, aging, and dying in a grand cosmic cycle. Galaxies become vast ecosystems of stars, with new suns igniting from collapsing clouds of gas, even as old ones flicker and fade. This ongoing cycle gives each galaxy a kind of heartbeat, a rhythm set by the cadence of star birth and star death. Over time, this galactic rhythm shapes the appearance and destiny of a galaxy, as it lights up with fresh stars and then is dimmed by their passing. It is an endless cycle of creation and destruction, giving each galaxy a form of life that persists through time. Not all stars keep the same tempo. Massive stars race through their lives in a few million years, exploding in their youth, while smaller stars, like red dwarfs, burn gently for tens or even hundreds of billions of years. Within a single galaxy, these different lifespans mean that at any given moment, some stars are just beginning, while others are coming to their end. It is as if a galaxy hosts both rapid drumbeats and slow, sustained notes in its stellar symphony. The most massive stars set a quick, dramatic tempo, brilliant crescendos with swift finales, whereas modest stars maintain a quiet, steady glow that can last through cosmic epochs. The death of stars often triggers the birth of new ones, perpetuating the cycle. When a great star detonates as a supernova, it sends out shock waves that can compress nearby clouds of gas. Those shocked clouds then collapse and give rise to a new generation of stars. In this way, the violent finale of one star can sow the seeds of many new beginnings. A galaxy's interstellar gas is constantly stirred and enriched by these explosions. Each supernova is like a drumbeat in the galaxy's story, a sudden, resounding event that momentarily energizes its surroundings, then fades. But in its wake, the galaxy's clouds carry new elements and momentum, setting the stage for yet more stars to spring forth. Sometimes the galactic rhythm speeds up dramatically. When galaxies interact or merge, their gas clouds are thrown together, often sparking enormous bursts of star formation. Two galaxies colliding can trigger a brilliant starbirth frenzy, with thousands of massive stars igniting in a relatively short span of time. These episodes, known as starbursts, are like the crashing cymbals of the cosmic orchestra, brief in the context of eternity, but spectacular in their intensity. For tens of millions of years, such a galaxy will blaze with an excess of newborn stars, as though the volume of its stellar music has been suddenly turned up. Eventually, the burst subsides, having transformed a huge amount of gas into stars, and the galaxy's heartbeat returns to a calmer pace. On a cosmic scale, the overall rate of star formation has had its own grand rhythm. Billions of years ago, the universe was much more prolific in making stars than it is today. Around 3 to 4 billion years after the Big Bang, an era astronomers call cosmic noon, star birth in galaxies peaked at a furious pace. Many young galaxies were gas-rich and produced stars dozens or even hundreds of times faster than the Milky Way does now. It was a time of galactic youthful vigor, when perhaps half of all the stars that exist today were forged. Since that peak, the universe's star-forming activity has gradually declined. In this quieter present age, galaxies have used up or locked away much of their free gas, and the average pace of star birth is a gentle echo of that earlier crescendo. Different galaxies also play different tunes. In grand spiral galaxies like our Milky Way, new stars still form steadily in swirling spiral arm nurseries, not as rapidly as in the distant past, but enough to keep the galaxy adorned with some young blue stars. Elliptical galaxies, by contrast, have very little cool gas left, and thus almost no new stars being born. They are like orchestras gone quiet, composed mostly of aging, reddish stars formed in the universe's earlier days. In many large galaxies, supermassive black holes in their cores have assisted in this quieting by erupting with energy that heats or drives away the remaining gas. Bereft of cool gas, such a galaxy can no longer birth new stars, its star-forming music effectively silenced. Some small dwarf galaxies experience intermittent star-forming bouts, followed by long lulls, like irregular drum beats in the cosmic symphony. Despite the variety, the underlying cycle of birth and death remains universal, threading through every galaxy regardless of shape or size. With each generation of stars, the composition of the universe grows richer. The heavy elements forged in successive star lives accumulate, enabling new kinds of celestial objects to form. Over billions of years, this gradual enrichment has allowed planets to coalesce around second and third generation stars, and complex molecules to arise in space. In this sense, the rhythm of star birth and death is also a progressive melody, building the complexity needed for life. Our own Sun is part of a later wave of star formation, born roughly 4.6 billion years ago in an already mature Milky Way. It carries heavier elements in its makeup: oxygen, carbon, iron, and more. The legacy of countless ancestral stars that lived and died before the Sun. The long, steady tempo of star cycles over cosmic time set the stage for Earth's formation and for living beings like us. We can witness these galactic rhythms in action, even today. In the Milky Way's sky, regions like the Orion Nebula shine as stellar nurseries, where fresh stars are being born amid swirls of glowing gas and dust. Elsewhere, we find the gauzy remains of long-ago supernovae. For example, the Crab Nebula, an expanding cloud of enriched debris marking where a massive star met its violent end. The Orion Nebula's cluster of infant stars and the Crab Nebula's filaments of stellar ash are living snapshots of the galaxy's life cycle. They show that the Milky Way, like all galaxies, continues to beat with the same timeless rhythm. Gas condensing into stars, stars exploding back into gas, in an endless, creative loop. Viewed from afar, a galaxy might seem serene and unchanging on the scale of human years, but over millions and billions of years, it pulses with activity. Stars flare into existence, shine for their allotted time, and eventually wink out or erupt in death, while new stars continually take their place. This cosmic rhythm, though slow and stately to us, is the very heartbeat of a galaxy. It ensures that galaxies are not static collections of ancient stars, but dynamic, ever-evolving systems. The steady turnover of stars is the ticking of time on a galactic scale, a profound reminder that even on the grandest stage, the dance of creation and destruction never truly comes to rest. Despite the immense scale of the universe, its early evolution was remarkably synchronized. Everywhere, more or less at once, the cosmic fireball cooled and gave way to atoms. Light burst forth, and then a great darkness fell. Later, the first stars ignited within a few 100 million years of each other across the cosmos. It's as though the universe had a single grand clock ticking off the milestones of creation, and all regions kept time with it. In this universal harmony, distant corners of space underwent the same transitions at nearly the same epochs. No matter how far apart two places were, they both experienced the clearing of the primordial fog and the dawn of starlight in tandem within the broad sweep of cosmic time. This synchrony has left an imprint we can observe today. The cosmic microwave background that now surrounds us has almost exactly the same temperature in every direction. Evidence that the entire young universe shared uniform conditions and acted in unison. Any 2 points in space, no matter how distant, released that primordial light at virtually the same moment once atoms formed. Likewise, when we look at galaxies billions of light years away, and thus see them as they were billions of years ago, we find them in similar stages of development as other galaxies that were their contemporaries. It appears that galaxies separated by vast distances nonetheless grew up together, following the same cosmic timetable. The cooling of matter, the formation of first stars, the assembly of galaxies, these events unfolded like a synchronized dance across unimaginable expanses of space. In the very early epochs, matter and energy were distributed so evenly that the flow of time was effectively universal. There were no massive objects yet to create strong gravity that would make time run differently from place to place. A second or a year on one side of the nascent universe would have been essentially the same as a second or a year on the opposite side. Space itself was young and coherent, and the concept of a shared cosmic time, the time since the Big Bang, was well defined and consistent everywhere. As eons passed, gravity introduced small local variations in the pace of time, but the overall expansion of the universe provides a common heartbeat that all galaxies still follow. Even now, long after those early ages, a sense of cosmic synchrony persists. Any astronomer in any galaxy, by measuring the microwave background or the oldest stars, would deduce a similar age for the universe. It is intriguing to imagine such an observer on a far-flung world in a distant galaxy, performing the same kind of measurements we do. They too would find that the omnipresent background glow has cooled to just a few degrees above absolute zero after nearly 14 billion years. They too might calculate that roughly the same vast span of time has elapsed since the cosmos began. Though separated from us by billions of light years, that hypothetical astronomer would arrive at a familiar answer: a universe of a certain age, evolving according to the same grand history. This shared timeline is a direct consequence of the early universe's uniform beginning and the way time has flowed universally since. This universal timekeeping is a legacy of the universe's hot, unified birth and the extraordinary flash of expansion, inflation that followed. It ensured that all observable parts of the cosmos started from nearly identical conditions and evolved in unison. Although separated by unimaginable distances, the early galaxies lit up in near unison, like a chorus of candles kindling around the same moment. The rhythm of cosmic events, the cooling, the lighting of first stars, the growth of galaxies, played out across space with astonishing coherence. The universe, in its youth, truly moved to a single cosmic tempo. As time went on, local differences gradually grew. A slightly denser patch of the universe would collapse a bit earlier to form a galaxy, while a slightly more rarefied patch lagged behind. But these were minor variations on the grand theme. In fact, the primordial irregularities in density were extraordinarily tiny, only fractions of a percent from one region to another. Yet over billions of years, they amplified to produce the rich diversity of structures we see today. Still, the major chapters of cosmic history were experienced by all parts of the cosmos more or less together. A universal sequence from the fiery beginning to the formation of atoms and the release of first light, to the birth of stars and the assembly of galaxies. When we gaze across billions of light years of space, we are effectively looking back in time at these shared chapters. A galaxy observed 10 billion light years away shows us how galaxies everywhere appeared 10 billion years ago. The synchrony of cosmic time allows us to read the universe's history directly in the heavens, because distance in space corresponds to age in time. On the largest scale, time flows onward uniformly, carrying every galaxy, every star, and every particle together into the future. That universal flow provides a common framework, a cosmic timeline on which all events find their place. It is humbling to realize that the clock that started at the Big Bang still beats steadily everywhere, and we on our tiny world measure our days and years against that vast cosmic backdrop. The seconds we count and the ages of galaxies both trace back to the same origin of time. So, the early cosmos moved in near-perfect step, its time flowing across all of space like a single sweeping story. As we leave behind the epoch of the first galaxies, we carry forward the concept of time that was born with the universe itself. Ahead lie new chapters of the cosmic tale. The formation of planets around second-generation suns, the cycles of time on those worlds, and perhaps the emergence of life able to mark the passage of days and seasons. The cosmic clock keeps on ticking, its hands moving from the realm of galaxies and stars toward the realms of planets and living beings. Time's story is far from over. The universe continues to learn how to count its seconds, and the next act will reveal ever more intricate ways that the cosmos keeps time. In the depths of cosmic history, time announced itself in grand gestures. The orbits of blazing stars, the birth and death of galaxies, each movement unfolding over eons. But within these vast expanses, another kind of clock was quietly ticking. As the universe cooled and expanded, matter condensed into its simplest, most fundamental units, atoms. And inside every atom, time found a new and steady beat, a pulse measured not in eons, but in the subtle vibrations of energy and structure. Within each atom, a tiny world unfolds. Electrons whirl in a haze around a compact nucleus, not like planets in a solar system, but in ghostly patterns defined by quantum rules. Yet even in their seeming randomness, there is order. Electrons can only occupy certain energy levels, and when they jump between these levels, they emit or absorb energy in precise amounts. That energy often takes the form of a particle of light, a photon, with a very specific color or frequency. These frequencies are nature's purest metronomes, unwavering beats at the heart of matter. Imagine an atom of cesium, deep in the darkness of space, minding its own ancient business. Within it, an electron transitions between two energy states in the blink of an eye, releasing a gentle pulse of electromagnetic waves. This particular transition in cesium happens with clockwork regularity, about 9 billion pulses every second. It is so consistent that, much later, humans chose it to define the length of a second. But long before any clocks or scientists existed, the cesium atom and every other atom kept up their ceaseless, silent ticking. Even when an atom isn't emitting light, it is never truly still. At any temperature above absolute zero, atoms jiggle and sway, a subtle vibration coursing through matter. In a solid crystal, billions of atoms are linked in an orderly grid, and together they can oscillate in unison like a microscopic choir. Consider quartz. Its crystalline structure allows it to vibrate at a steady frequency when energized, acting like a tiny tuning fork. This too is a natural rhythm of matter, so reliable that one day it became the beating heart of countless clocks, keeping time with every vibration. In every corner of the cosmos, these atomic rhythms play out in unison. A hydrogen atom on the far side of the galaxy dances to the same tune as a hydrogen atom on Earth. The light from distant stars carries these familiar frequencies, each spectral line a testimony that an atom's tick is the same everywhere. This unity of atomic time is one of nature's wonders. A cesium atom in a laboratory, a hydrogen atom in a nebula, all keep time with the same steadfast beat. It is a subtle music, inaudible yet pervasive, underlying the apparent chaos of the universe. As steady as atomic time is, atoms themselves are not immortal. Many may remain unchanged for billions of years, but some harbour a restless energy deep in their core. Within certain atomic nuclei, forces build quietly until, one day, the nucleus lets go, breaking apart or changing form. In those hidden cores, a different clock is ticking down, the clock of radioactive decay, measured not by vibrations, but by lifetimes. Far beyond any single atom, in the hearts of stars, trillions upon trillions of atomic nuclei collide and merge. Each fusion is like a beat in a star's life, consuming fuel and releasing energy. These reactions create new elements and flood the cosmos with starlight, setting the tempo of a star's lifespan. Thus, from the quiet tick of electrons to the roaring furnace of nuclear fire, matter pulses with the passage of time at every scale. In the core of every star, atoms are pressed and forced into union. Hydrogen, the simplest element, fuses into helium under the star's immense gravity, releasing light and heat. Each fusion reaction is like a heartbeat, the star's energy pulsing outward in waves. These pulses are too rapid and numerous to count individually, but together they establish the rhythm of a star's life. As long as the fuel lasts, the star's beat goes on, steady or erratic depending on its nature, but each tick marked by the alchemy of fusion. Not all stars keep the same tempo. A small red dwarf, cool and dim, sips its fuel slowly and can burn for trillions of years. A gentle, slow heartbeat that could outlast entire galaxies. A massive blue giant, on the other hand, lives in frantic fury. Its core fuses fuel at a blistering pace, a drumroll of reactions that exhausts its life in a few million years. Our own sun's heart beats in a comfortable middle range, set to shine for around 10 billion years in total. In each case, the mass of the star sets the pace of its life, from the languid throb of the smallest stars to the fevered pulse of the giants. Some stars even literally pulse, growing brighter and dimmer as their layers expand and contract in a regular rhythm. These are the variable stars, cosmic beacons, whose rhythmic brightening and dimming act as natural clocks visible across space. The periodic pulse of a Cepheid variable star, for instance, can be as reliable as a ticking pendulum, allowing astronomers to measure distances in the universe. In the vast darkness, these stars are like lighthouses, their brightness oscillations keeping time on a galactic scale. Each cycle of dimming and glowing is like the second hand on a cosmic clock, marking the passage of time in the star's life. But even the most patient star eventually runs out of fuel. When a star's core has fused as much as it can, the steady beat falters and a final act begins. For some, like our sun, it means swelling into a red giant, a slowing, final drum roll before gently shedding its outer layers. For others, the great massive stars, it means a catastrophic finale, a supernova explosion, the star's heart stopping in one brilliant, violent instant. In that moment, time for the star effectively comes to an end, but the debris it scatters is full of new elements, flung into space to seed future stars and planets. Those new elements born in stellar furnaces carry within them their own ticking clocks. Uranium, for example, created in the chaos of a supernova, is a heavy atom with a subtle instability. It doesn't live forever. Instead, it decays slowly, turning into lead over billions upon billions of years. The moment a uranium atom is forged, an internal timer starts counting down its half-life, though no one can predict the exact moment any single atom will change. Scattered across the cosmos and later built into young planets, these long-lived atoms become nature's time capsules. Radioactive decay is a quiet, statistical beat. At every moment, each unstable nucleus has a chance to fall apart, to release a bit of energy and transform into something new. For a collection of countless atoms, this chance becomes a steady rate, a half-life, the time it takes for half of the atoms to have decayed. Some substances have half-lives measured in split seconds, a furious ticking that quickly exhausts itself as the element vanishes. Others, like uranium or thorium, have half-lives so long that they are still ticking from the day the Earth coalesced, billions of years ago. The range of lifetimes in the atomic world is staggering. There are isotopes that exist for only the briefest blink. Their nuclei break apart almost as soon as they form, a mayfly existence on the atomic scale. And at the other extreme, some atoms endure with hardly any change across the entire history of the universe. One rare isotope, xenon-124, has a half-life trillions of times longer than the universe's age. Its decay is so slow, it was only recently observed by catching a handful of atoms in the act. In between these extremes lie the familiar clocks of the atomic world, each isotope ticking at its own pace. In a way, every piece of radioactive material is a gathering of tiny clocks. They don't tick in sync, but their collective decay keeps time with remarkable reliability. A lump of carbon-14, formed in Earth's atmosphere and taken up by living creatures, will start losing its atoms at a predictable rate once those creatures die. After thousands of years, enough of it decays to reveal how long ago that organism lived, acting as a natural timestamp. Similarly, crystals growing in cooling magma trap radioactive elements. From the moment they solidify, their internal isotopes begin the slow count that will tell the story of the crystal's age. Fusion and decay, one blazing with energy, the other quietly ticking away, are both part of the cosmic symphony of time. Fusion powers the stars and defines their lifetimes, while decay turns individual atoms into timekeepers long after those stars are gone. Through fusion, the universe has a heartbeat. Through decay, it has memory. The elements themselves, born in cosmic fire or in the warm glow of stars, carry on to become the clockwork within planets and moons. As these time-bearing elements collected into young planets, a new chapter of timekeeping was poised to begin. In the early Earth, the heat of radioactive decay kept the world molten and restless. But gradually, the planet cooled. A solid crust formed, and with it came the first enduring rocks. Inside those rocks, the ticking of radioactive atoms continued, and now their slow transformations could serve as clocks, quietly stamping moments into Earth's nascent memory. For the first time, a planet could retain a history of itself. The surface of Earth, once a blank slate continually reshaped by fire, began to preserve evidence of what had come before. Each layer of sediment, each band of hardened lava, was like a page in a growing diary. Time, which had always been present in the dance of atoms and stars, now left visible traces in stone. Geological time had begun. The Earth was learning to remember. For ages after its fiery birth, Earth could not keep a record of its own story. The young planet was a molten orb bombarded relentlessly by asteroids and comets, its surface constantly remade by impacts and volcanic fury. In those tumultuous early days, any crust that formed was quickly destroyed, erasing the slate again and again. But as the bombardment waned and the planet gradually cooled, Earth at last gained the ability to remember. The first long-lived crustal rocks crystallized from ancient magma, and the planet's journal of stone began to write itself. Tiny crystals of zircon, some over 4 billion years old, are among the earliest words in Earth's story. These hardy minerals weathered the planet's violent youth and survived, embedded in younger rocks, like time travelers from a lost era. From them, we learn that by 4.4 billion years ago, mere hundreds of millions of years after Earth formed, there was already solid ground and even liquid water. Those resilient zircons carry whispers of rain and oceans in a time no other rocks have preserved. In their atomic makeup, they hold the signatures of that earliest chapter, a memory of a world just beginning to cool and calm. Beyond those tiny scattered clues, the more continuous rock record picks up a little later. By about 4 billion years ago, we find the first large stretches of crust that survived. Ancient Canadian shield rocks and Australian outcrops still stand today as remnants of Earth's early continents, like the faded pages of a very old book. Layer by layer, new rocks formed, and some persisted. Every volcanic eruption that cooled into solid stone, every sediment that settled in an ocean bed, had the potential to become part of the growing chronicle. Over immense spans of time, these processes built up archives of stone, preserving sequences of events: the rising of mountains, the opening of oceans, the slow dance of continents. Earth's geologic memory is exceptional among the planets. The Moon, Mars, and Mercury bear ancient scars, craters frozen in time, but they lack Earth's ever-renewing layers of rock and rich cycles of erosion and deposition. On those worlds, the record is static and sparse, limited to eras long past when volcanic or water activity occurred. Earth, in contrast, is restless yet conserving. Its surface transforms and recycles, yet manages to archive fragments of the past. It is as if Earth writes its autobiography on reused parchment, layering new words over old, but never completely blotting them out. By generating new rocks while preserving some of the ancient ones, our planet accumulated a mosaic of memories that extends across nearly 4 billion years. As time went on, Earth refined its memory keeping. Sedimentary rocks, layers of sand, silt, and clay laid down in water or wind, captured snapshots of the environment with remarkable fidelity. Each layer of sediment in a quiet lake or on a seafloor could record a season, a year, or 1,000 years of gradual deposit. In those layers are clues to conditions long ago. The size of grains might speak of calm waters or raging floods. The chemical makeup might whisper about the oxygen in the air or nutrients in the water. Year by year, layer by layer, sediments settled and turned to stone, forming a stacked timeline. The deepest layers are the oldest, the upper layers younger, each stratum a page of history. Together, they form a chronological record that a trained eye can read like chapters in a book. In some places, the layering became rhythmic. In cool climates, for example, lake sediments formed varves, alternating light and dark bands corresponding to the annual cycle. A light, coarse layer might accumulate in spring and summer, when melting snow swells rivers, followed by a dark, fine layer in winter, when waters calm and fine particles settle. Each paired band is the signature of a single year in mud and clay. Counted carefully, varves provide an annual diary reaching back tens of thousands of years, like tree rings preserved in stone. In caves, too, mineral layers grew slowly on stalactites and stalagmites, each ring of calcite recording the drip rate of water through seasons of rain or drought. The planet was not only remembering broad epochs, but also the delicate pulse of years. Earth's rocky archives also preserve the marks of cataclysms. Now and then, a thin band of clay in the sedimentary record may hold traces of an ancient disaster. A brief story of upheaval captured between ordinary years. One such layer, found worldwide at the boundary between the Cretaceous and Paleogene periods, is rich in the element iridium and soot. It marks a day, 66 million years ago, when a massive meteorite struck the Earth and wrought sudden devastation, ending the age of the dinosaurs. That thin grey layer is a memory of darkness and fire that spread across the globe. Similarly, bands of volcanic ash in rock layers speak of titanic eruptions in the distant past, and layers of abruptly changed fossils indicate times of extinction and rapid change. Each of these is a bookmark in Earth's story, pointing to a moment when the usual rhythms were interrupted by something extraordinary. As life evolved, the Earth's rock record became a tapestry woven with biological threads. The remains of organisms, shells, bones, leaves, even bacteria, were entombed in sediments and preserved as fossils. Through these, the planet remembers not just the physical events like eruptions and floods, but also the living inhabitants of each era. A limestone bed might hold an ancient coral reef. Every coral and shell, a chapter of life's history written in stone. A coal seam might be the compressed remains of a swamp forest, its leaves and logs telling of lush, carbon-rich swamps that existed long before humans. Fossils allowed Earth's memory to include characters and plots. The rise and fall of species, the ebb and flow of ecosystems, the great innovations of evolution, and the tragedies of mass extinctions. Geologic time, as revealed by these records, dwarfs our human perspective. To grasp it, one must stretch the imagination across millions and billions of years. Entire mountain ranges rise to towering heights and erode away to gentle hills in spans that are almost geologic instants. Vast inland seas appear and then vanish, leaving salt and fossils behind. Ice sheets advance and retreat, scraping landscapes flat and then melting, all over cycles of tens of thousands of years. Standing before a towering cliff of stratified rock is like looking at the calendar of deep time. Each stripe of rock represents an epoch, each boundary a transition, cumulatively recounting a story that vastly predates humanity. It is humbling and awe-inspiring to consider how patiently the Earth has recorded time. A human life might read only a sentence or two of this immense book, yet we now know that beneath every forest and city, under every desert and ocean, lie archives of stone that remember ages we never saw. The Earth keeps its own counsel, indifferent to the brevity of our experience. And still, we have managed to decode some of its language. Through science and curiosity, we learn to read the records in the rocks, to hear the echoes of ancient rivers, volcanoes, and seas. The planet's long memory has become, in part, our memory as well. For billions of years, this grand chronicle remained unread, its meaning known only to time itself. But eventually, on Earth, there arose observers with the curiosity to decipher it. The memories in stone, patiently recorded over eons, were waiting for someone to listen. In time, the clock hidden in the Earth's crust would be discovered, and with it, the story of the planet's deep past would be pieced together. For centuries, people have marveled at the layers of rock exposed in cliffs and canyons, intuitively sensing that these strata were old, perhaps unimaginably old. The idea that the layers themselves marked the passage of time was a revelation that dawned slowly. By the 18th and 19th centuries, naturalists began to realize that the lowest layers must be the oldest and the top layers the youngest, implying a great span of time with no human witness. Fossils embedded in these rocks showed distinct forms of life in different layers, suggesting that whole worlds had come and gone. The Earth's crust was recognized as a timeline, a record of sequential chapters in Earth's history. This was the first glimpse of deep time, a past stretching far beyond the scale of human memory. This understanding was revolutionary. The familiar view of a world only a few thousand years in age gave way to one of practically infinite antiquity compared to human life. Observers like James Hutton looked at tilted rock layers in Scotland and saw no vestige of a beginning, no prospect of an end. It was dawning on science that the Earth's story might span millions upon millions of years. Yet even as these thinkers grasped the immensity of geologic time, they had no way to assign precise ages to the rocks. They could discern relative order, this came before that, but the clock's numbers were missing. The rock record was a grand timeline without any dates. The breakthrough came from deep within the atom. At the turn of the 20th century, the discovery of radioactivity unveiled a natural clock embedded in minerals. Certain elements, like uranium and thorium, were found to slowly change into other elements at a fixed rate. A uranium atom trapped in a rock will, after a known average span, decay into lead. This happens spontaneously, like a tiny hourglass slowly dripping sand from one side to the other. Scientists realized that if they could measure the amounts of the original radioactive element and its decay product in a mineral, they could calculate how long that process had been going on. In other words, the mineral could reveal its own age. Imagine a mineral crystal forming in the cooling crust of a new rock. At the moment it solidifies, it might contain a certain amount of radioactive uranium and virtually no lead, since lead is the end product of uranium's decay. The instant the crystal locks in those uranium atoms, the clock starts. Over eons, the uranium atoms slowly decay. A few of them turn into lead each year, like single grains of sand falling in an hourglass so large it runs for billions of years. After a long span of time, if that crystal is still preserved and we retrieve it, we might find, say, half of its original uranium has become lead. Knowing the half-life of uranium, we could infer that the crystal has been ticking for about 4.5 billion years. In this way, the rock itself divulges the number of years it has been a part of Earth. When geologists first applied these radiometric techniques to Earth's oldest rocks, the numbers that emerged reshaped our understanding of the world. Measurements from ancient minerals all converged on an Earth that is roughly 4.5 billion years old. Tiny zircon crystals from Australia, cratonic rocks from Canada and Africa, fragments of meteorites that fell to Earth, all bore the same message, give or take a few million years. Our planet is over 4 billion years in age. This was far beyond the most liberal estimates of the pre-scientific imagination, and yet it was written so clearly in the rocks that it could not be denied. The Earth, we learned, is ancient on a scale that truly staggers the human mind. With the ability to read absolute ages, the geologic timescale became more than a relative timeline. It became a quantified history. The divisions of Earth's past, once based only on characteristic fossils and rocks, were now assigned dates. We learned that the dinosaurs died out 66 million years ago. that the great coal-forming swamps of the Carboniferous flourished around 300 million years ago, that the vast ice ages of the Precambrian ended about 600 million years ago, allowing complex life to bloom. Events that were once just ancient could now be placed in a calendar of deep time. It was as though the Earth's diary, long suspected to be vast, had finally been translated and annotated with dates and times. Tracing time through Earth's crust also linked our planet's story to that of the entire solar system. By dating meteorites, pieces of asteroids that fall to Earth, scientists determined that the solar system itself coalesced around 4.5 billion years ago. The ages of lunar rocks, brought back by astronauts, showed that the moon's surface solidified soon after, roughly 4.5 billion years ago. Together, these discoveries wove Earth's timeline into the broader tapestry of our cosmic neighborhood. Our planet's clock started not long after the sun's birth, situating Earth's beginnings within the context of a forming solar system filled with other worlds. Equipped with these measurements, we also began to grasp the age of the universe itself. The techniques honed on Earth's rocks provided a stepping stone to estimating the time since the Big Bang, using distant stars and cosmic expansion. Having learned how to measure billions of years on Earth, our minds could better grapple with the idea that the cosmos might be around 13.8 billion years old. In a sense, reading the clock in the rocks was a training ground for reading cosmic time. By understanding the deep past recorded underfoot, humanity was prepared to seek answers in the stars, tying together the story of Earth with the story of everything. Moreover, Earth's crust contains not just one clock, but many. Different radioactive isotopes serve as check marks that cross-verify each other. Uranium-lead dating might tell us a zircon's age, while another method, like potassium, argon dating, might date a volcanic ash layer above it. If both agree, confidence in the timeline grows. In younger rocks, carbon-14 clocks measure hundreds or thousands of years, useful for archaeology and the recent past, while other isotopes fill in the gaps between. Each method is like a different hand on a clock, one for hours, one for minutes, one for seconds, covering different spans of time, but all part of the same timepiece. The remarkable consistency of results from these methods tells us that the clocks have kept true. Nature's timekeepers are reliable, and through them, we have learned to tell time on scales far beyond our own lifetimes. Beyond radioactivity, geologists found other, subtler clocks in Earth's layers. The magnetic minerals in volcanic rocks, for example, retain a record of Earth's magnetic field direction at the time they cooled. Every few 100,000 years, our planet's magnetic field flips, north becomes south, and this reversal is captured like a timestamp in solidified lava. By counting these magnetic stripes on the ocean floor, we gauge the pace of seafloor spreading and thus measure the age of ocean basins, the oldest, of which are only about 200 million years, continually recycled by plate tectonics. In Greenland and Antarctica, cores drilled through ice reveal annual layers, compacted snow from each year, going back hundreds of thousands of years, a frozen timeline of climate and atmosphere. Even tree rings in petrified wood, or growth bands in fossil corals, have given us counts of days per year in ancient times, revealing that Earth's rotation has gradually slowed. In the distant past, a year fit in over 400 shorter days. All these pieces of evidence interlock, each one a partial clock that, together, give us a rich account of time's passage. That we can peer billions of years into the past by using a bit of crystal or a layer of rock is a testament to human curiosity and ingenuity. The inert stones beneath our feet turned out to be storytellers after all. They just spoke in the language of isotopes and strata, which we learned to translate. Now we stand on the Earth and can say, with wonder and certainty, how old things are. We can trace the arc of time from the primordial crust to the present landscape. The clock in the rocks, once a mystery, has become an open secret. And with that knowledge, we see our world not as a static stage, but as a dynamic being that has lived through vast ages and changes. Yet, while rocks keep time in their patient way, another set of timekeepers has always been in motion above us. The Earth's rotation and orbit, and the Moon's monthly journey, were marking time long before we understood them. In fact, the regular movements of the heavens provided the first rhythms that early humans and all life could directly observe. To truly appreciate nature's calendar, we must look up from the stones and into the sky, to the dance of orbits that orchestrates the cycles of days, months, and years. Every turning of the Earth on its axis brings the transition from day to night, the most immediate and palpable cycle we experience. This simple rotation, taking about 24 hours to complete, establishes the fundamental beat for life's daily activities. Long before any clocks existed, the alternation of light and darkness was a universal metronome. Since the dawn of life, organisms have been exposed to this rhythm, the warmth and illumination of day, followed by the cool and dark of night. The day-night cycle is so reliable and so ingrained that it became the foundation for countless biological processes and behaviors. Meanwhile, as Earth spins, it also moves through space on a grander circuit, our yearly orbit around the Sun. One trip around takes roughly 365 days, and in that time, the tilt of Earth's axis causes sunlight to fall unevenly over the year, creating the seasons. This annual voyage is a slower rhythm than the daily spin, but its effects are profound. The lengthening days of spring coax flowers from the ground. The waning light of autumn signals leaves to fall. In winter, one hemisphere cools under short days, while the other enjoys summer's long, sunny hours, and then they trade places. This cycle of seasons repeats with such regularity that it has served as a calendar for life itself. The migration of animals, the dormancy of plants, and countless other patterns are tuned to the year's progression. Circling around Earth is our Moon, whose own orbit takes about 4 weeks to complete. As the Moon travels, we see it go through phases: new, crescent, half, full, and back again. A gentle, mesmerizing clock in the night sky. For early humans, the waxing and waning moon was likely the first way to mark time shorter than a year. A month, loosely based on the lunar cycle, became another natural unit of time. The moon's influence extends beyond light. Its gravity tugs at our oceans, causing tides to rise and fall in a regular cadence. In most places, 2 high tides and 2 low tides occur each day, roughly 6 hours apart, following the moon's inexorable pull as it circles Earth. This rhythmic breathing of the sea, high tide, low tide, is one of nature's most reliable clocks, especially along the coasts. The motions of Earth and Moon are not random. They form a cosmic clockwork that has kept steady time over the ages. Johannes Kepler discovered that planets sweep around the Sun in ellipses, speeding up and slowing down in predictable ways. Isaac Newton explained these movements with the universal law of gravitation. Because of these laws, an Earth day isn't just approximately 24 hours. It's almost exactly so, varying by mere thousandths of a second over centuries. The year, too, is consistent, down to the hour, aside from tiny shifts over millennia. The moon's orbit and the timing of tides can be calculated far into the future or the past. In short, the celestial dance is a precise one. It provides a framework of repeating intervals, the basis for what we call calendars. Nature gave us this scaffold of time, and human cultures eventually built their schedules upon it. Beyond the everyday cycles, there are longer orbital rhythms that unfold over tens of thousands of years. Earth's tilt wobbles slightly, the shape of its orbit stretches and shrinks, and the planet even gyrates like a slow top, tracing a circle in the sky, a motion called precession. These changes, collectively known as Milankovitch cycles, modulate Earth's climate on long timescales. When certain cycles align, summers become a bit cooler and winters a bit milder, or vice versa, tipping the balance toward the growth or retreat of great ice sheets. Over the last few million years, these celestial rhythms have paced the timing of ice ages. Though subtle to our eyes, they are recorded in geological clues, in the alternating layers of ocean sediments and ancient ice that show a pulse of warm and cold epochs. The grand dance of Earth's orbit, thus, not only marks years, but subtly steers the planet's environments over ages.
For life on Earth, all these astronomical cycles form the backdrop of existence. The turning of the planet, the circling of the moon, the swing around the sun. These are the metronomes to which living things have adapted their behaviors and internal clocks. Over billions of years, organisms that aligned themselves with day and night, with the seasons and the tides, had an advantage in survival. The spin of Earth determined when it was light to find food or dark to hide. The orbit determined times of plenty and times of scarcity. The moon dictated when coastlines would be submerged or exposed. Life's evolution became intertwined with these patterns. In a sense, Earth's orbit and rotation imprinted themselves onto life's DNA, programming creatures with routines that match the cosmic schedule.
Under the sun's daily rise and setting, the most fundamental rhythm for living creatures emerged, the circadian rhythm. Almost every organism has one, a built-in, roughly 24-hour cycle attuned to day and night. Even tiny cyanobacteria in primordial oceans had genes that turned on with the morning light and off at dusk. To this day, flowers unfurl their petals at dawn and close them at twilight, following an internal clock. Our own human bodies feel the sway of this cycle. Hormones that wake us crest in the morning light, while those that make us sleepy surge in the darkness of evening. The consistency of Earth's rotation allowed life to evolve this dependable internal timing, a synchronization with the planet's spin that persists even if an organism is taken far from its normal environment. Just as many creatures live by day, others have carved out the night. Nocturnal beings, from moths fluttering in moonlight to desert foxes prowling under starlit skies, run on a shifted schedule. Their eyes, ears, and habits are tuned to darkness. Bats leave their roosts at dusk to chase insects whose own cycles bring them out after sunset. Owls, with keen night vision, silently hunt in the hours when most other birds are asleep. These creatures still possess circadian rhythms, but their clocks tell them to sleep when the sun is up and to live when it's down. The moon and stars become their guides. A bright full moon might give enough light for a midnight forage, whereas a moonless new moon night invites different strategies. Thus, life has filled both halves of the diurnal cycle, the solar day and the lunar lit night, each realm flourishing in its allotted time. Life's calendar extends to the yearly cycle as well. The annual march of the seasons has orchestrated countless natural events. In spring, as days lengthen and temperatures rise, hibernating animals awaken from their long sleep and migratory birds return from their journeys. Forests that were barren in winter explode into green. Many animals give birth in spring, timing the arrival of their young to coincide with the abundance of food and the gentle weather. As the year progresses to summer, life revels in warmth. By autumn, signals of change appear. Daylight wanes, leaves change colour and fall, animals build up reserves or prepare to travel. When winter arrives, a hush falls in many parts of the world. An ice-bound interlude, a test of endurance until light and warmth grow again. These patterns have repeated over and over, and species have evolved to meet them. Some grow thick fur for winter and shed it for summer. Some enter diapause or dormancy to wait out the cold or dry season. The cycle of the year is an ancient drumbeat to which living things have choreographed their existence. The moon's influence on life is more subtle, but no less real. In the ocean, corals synchronize their reproduction by the lunar cycle. On a few special nights a year, often just after a full moon, corals on a reef will simultaneously release tiny bundles of eggs and sperm into the water, turning the sea into a blizzard of potential life. This mass spawning ensures that gametes meet in the open water, and by coordinating with the moonlight and tides, corals maximize the odds of fertilization while minimizing the chance of predators devouring all the offspring. On beaches, small silver fish called grunion have a remarkable mating ritual tied to the moon. Around the highest tides of the full or new moon, grunion ride the waves onto shore by the thousands. The females quickly bury themselves in the wet sand to lay eggs, while males wrap around them to fertilize. Then the fish wriggle back to the retreating water. The eggs remain hidden in the sand, safe from most predators, until the next high spring tide about 2 weeks later, when the hatchlings are washed out to sea. In this way, the moon's cycle provides a schedule for reproduction. Even birds and other animals can be moon timers. High in the mountains of Réunion Island in the Indian Ocean, an endangered seabird called Barrow's petrel uses both the sun and the moon to plan its travels. These petrels spend months at sea, but return to their nesting colonies each year at a very precise time, around the full moon nearest the start of the breeding season. It appears they gauge the length of daylight to decide the season, and then use the full moon as a rendezvous signal to all arrive at once under its light. In countless subtle ways, species have evolved to notice the moon's phases, a nightly cue that the Earth's satellite is cycling as predictably as the turning of a gear. Perhaps the most tangible interplay of lunar and life rhythms is along the seashore, where tides rule. The intertidal zone, alternately submerged and exposed, teems with creatures uniquely adapted to that oscillating environment. Crabs scuttle to follow the water's edge, avoiding drying out. Clinging mollusks shut tight and wait patiently through the hours of air until the sea returns. Some marine worms time their emergence from the sand with specific tides, ensuring they find mates at just the right moment when the water is calm and the phase of the moon is just so. These patterns are so ingrained that if you take a tide pool creature away from the ocean and keep it in a laboratory tank, it may still get active at the times corresponding to the tides of its home shore for a while, as if carrying an echo of the ocean's rhythm within it. Over longer timescales, the moon has played an unsung role in Earth's habitability, and thus in life's endurance. Our moon is unusually large relative to Earth, and its gravitational pull has stabilized Earth's axial tilt. This means that unlike Mars, which wobbles more dramatically, Earth's seasons have remained fairly steady over eons. Without the moon, scientists suspect our planet might have experienced chaotic swings in orientation, leading to extreme climates that could shift from sweltering to icy in geologically short order. But thanks to our lunar companion, Earth's climate rhythms have been more regular. allowing life to adapt and thrive without facing constant, unpredictable upheavals. In a very real sense, we owe the gentle, life-friendly pacing of our seasons to the moon's steadying presence, a cosmic guardian of Earth's timekeeping. Life's rhythms, born of cosmic cycles, are deeply embedded. Even when we try to ignore them, our bodies and minds are tuned to those ancient metronomes. Ask anyone who has flown across the world and experienced jet lag. Our internal clock struggles when detached from the external cycle of day and night. We try to live by our schedules and artificial light, but a part of us still longs for morning sunshine and the quiet of night. In remote areas, away from city lights, people often find their sleep synchronizing with the sun. Tired after sunset, awake at dawn. We are modern creatures with technology and electricity, yet physiologically, we remain children of Earth's rotation. Humans, in fact, have always been aware of these natural rhythms, building our earliest timekeeping practices around them. The first calendars were likely observational, marking the return of migratory animals or the flowering of certain plants as signals of spring, noting the earliest sunrise or the first frost. Many ancient structures, from Stonehenge in England to medicine wheels in North America, are thought to align with the solstices or equinoxes, acting as gigantic calendars to herald the turning of the year. Our ancestors told time by the sky, a month by the moon, a day by the sun's journey, a year by the stars' shifting position at dusk. Festivals and rituals world over, whether harvest celebrations or New Year observances, are timed to celestial events, honoring the innate calendar that nature provides. Even on a personal level, we feel a kinship with the cycles above. The full moon's bright face has inspired stories, myths, and wonder since time immemorial. Terms like moonstruck or full moon fever reflect an enduring intuition that the moon stirs something in us, though science finds little evidence for any strong effect. The tides of emotion we attribute to the moon might be more poetic than literal, but that poetic connection is a sign of how deeply the moon is woven into our collective imagination. Its regular cycle, dependable yet ever-changing, mirrors our own lives in symbolic ways. Phases of growth, fullness, and decline, then quiet darkness before the cycle begins anew. After billions of years, in which time on Earth was kept only by the unconscious cycles of nature, time has now found a consciousness. We humans are part of life's fabric, born with the same circadian beats and seasonal pulses as any creature. But we have also become observers and thinkers, turning a curious eye back onto the processes that shaped us. We learn to recognize the patterns, to predict them, and then to formalize them. We invented our own timekeepers, sundials that track the sun's shadow, calendars to tally the days of the year, eventually mechanical and atomic clocks that tick away the seconds with extraordinary precision. In doing so, the universe, through us, has gained the ability to count its own moments. The transformation is profound. The impersonal turning of planets and the vibration of atoms have led to beings who not only experience time, but measure it, divide it, and ponder its meaning. The story so far has been about time's natural manifestations, the pulse of matter, the rhythms of earth and sky, the beat to which life dances. Now, that story will move to a new realm, the conscious mastery of time. The descendants of those early life forms, shaped by eons of cosmic cycles, will take time into their own hands. They will create clocks inspired by the swing of pendulums and the oscillation of quartz, and they will seek to understand time at its most fundamental level. The universe has learned to tell time through us, and in the next part of our journey, we will explore how that knowledge has been used to change our world. The world turns quietly under a pale dawn sky. Long before any clock or calendar existed, time still flowed in the gentle rhythm of day and night. The first living creatures rose and rested with the rising and setting of the sun. Each new day brought light and warmth. Each night, darkness and rest. Life began to follow this cycle, guided by the endless turning of the earth. In the primeval ocean, billions of years ago, even simple organisms sensed the coming of day. Tiny photosynthetic microbes drifted in the water, awakening at first light to soak in the sun's energy. When darkness fell, they slowed and conserved their strength until dawn returned. Though they had no eyes to see the sun, their bodies were tuned to its rise and fall, an ancient harmony between life and the turning earth. In those distant times, a day on Earth was shorter than today. The young planet spun faster on its axis, and sunrise to sunrise might come and go in only 18 or 20 hours. Over the eons, Earth's rotation gradually slowed, stretching the length of the day. Life's internal rhythms stretched as well, adapting little by little to the leisurely 24-hour pace we know now. Even on the scale of billions of years, living creatures kept in step with the changing heartbeat of the planet. Time's rhythms came not only from the sun, but from the moon as well. Along rugged coastlines, the ocean's tides rose and fell in a steady cycle. Every day, the sea pulled back and then rushed in, following the lunar clockwork. Creatures in tide pools and on beaches adapted to this schedule. Clams burrowed deep as water retreated and emerged when the waves returned, while tiny crabs scurried to feed at low tide. Life learned to move with the pulse of the tides, another hidden clock set by the celestial dance of moon and earth. Far out at sea, countless tiny creatures followed their own daily journey through darkness and light. Each evening, as the sky grew dim, vast swarms of plankton rose from the depths toward the surface waters. Under the cover of night, they feasted near the surface. Before dawn's first glow, they drifted back down into the safety of deeper gloom. This immense vertical migration, repeated every day by billions of ocean beings, shows how profoundly the cycle of day and night guides life's motions, even in the deepest blue wilderness. On land, plants learn to count the hours of light. In a quiet forest, a flower opens its petals with the morning sun and closes them at dusk, as if bowing out for the night. Even if kept in endless darkness, some flowers still quietly open and close on schedule, obeying an inner clock. There is no conscious thought in a plant, yet it follows time's invisible instructions, written into its very cells. Animals, too, live by the earth's daily rhythm. At first light, a chorus of birds begins to sing from the trees, as if celebrating the new day. They often stir moments before sunrise, guided not merely by the growing light, but by an internal sense that morning is near. In the pre-dawn stillness, a rooster crows to announce the coming day, even if no hint of sunlight has yet touched the sky. And when evening falls, creatures large and small grow drowsy and slip into sleep, their bodies knowing that the time for rest has come once again. Yet for some, night is when life awakens. As dusk deepens, owls open their keen eyes and take wing in search of prey under the cover of darkness. Bats flutter out of their caves at twilight to chase insects in the warm night air. In a moonlit desert, nocturnal flowers unfurl, releasing perfumes to attract midnight pollinators. These creatures of the night live opposite lives to those of the day, showing that life has filled every hour with its presence. Some hearts beat fastest under the sun, and others under the stars. Hidden inside every living creature is a clock with no face and no hands. This biological clock keeps time in the language of cells and sunlight, of hormones and heartbeats. It ticks away silently, aligning an organism's activities with the cycle of day and night. Life does not just react to the sunrise and sunset. It anticipates them, guided by this inner metronome that never stops. Through this internal rhythm, a bird knows to begin its morning song just before the first light, and a flower knows to start unfurling at dawn's approach. These actions are not mere responses to what is happening in the moment. They are preparations for what is about to happen. The living clock tells a creature that morning is coming, so it should get ready to wake, to feed, or to sing. And as day turns to night, the same hidden clock slows the creature's pulse and stirs it toward rest, long before darkness fully falls, ensuring it is safely at roost or den when the world goes dark. Within the human body, this subtle clockwork orchestrates countless processes. In the hours before dawn, our body temperature gently sinks to its lowest point, and our muscles rest in their deepest slumber. As morning approaches, our heart begins to beat a little faster, and hormones flood our bloodstream to draw us toward wakefulness, stirred by a dawn we do not yet see, but already feel. By early afternoon, our energy peaks, and as evening comes, the body's chemistry shifts again. The pulse slows, and sleep-promoting signals rise like soft music at dusk, coaxing us toward rest. All of this happens on cue day after day, usually without our noticing, directed by an inner timekeeper. The internal timing of life is remarkably steadfast. There have been those who sought total isolation from the cues of day and night, researchers who sealed themselves in dark caves, far from any clock or sunlight, to see how the body would react. In one such cavern, deep underground, a man lived for months with no sun to mark day or night, only the dim glow of a lantern to light his world. And yet, he found that his body continued to slip into sleep and awaken on a roughly 24-hour cycle. His meals, his alertness, even his moods ebbed and flowed in a familiar daily pattern. Without any outside signal, his internal clock kept on ticking in the dark, drifting slightly but never losing its rhythm, a testament to nature's built-in timekeeping. This innate daily cycle is so universal that it has a name, the circadian rhythm, meaning around a day. It courses through nearly every living thing, from the simplest bacterium to the tallest tree to us. In mammals like ourselves, a tiny cluster of cells in the brain serves as the master clock, coordinating the rhythms of hunger, sleep, and energy. Yet even individual cells in the body carry their own tiny ticking mechanisms. Heart cells, liver cells, skin cells, all following daily patterns. The master clock keeps them in unison, like a conductor leading an orchestra, so that the whole body moves smoothly through the 24-hour symphony of life. With these internal clocks, life can keep time automatically. But time's influence on living beings does not end with these unconscious rhythms. In creatures with more complex minds, time takes on new dimensions. It lives in the memory of the past and in the anticipation of the future. The biological beat of the circadian clock continues quietly in the background, while in the foreground of the mind, an animal can remember yesterday and sense tomorrow. The story of time now moves from the ticking of cells to the realm of thought and instinct, where the notion of yesterday first begins to take shape. Under a burning savanna sun, an elephant matriarch leads her herd on a long, determined march across the dry plains. She walks with purpose toward a spot beyond the horizon, guided by more than instinct. Years ago, during another drought, she drank from a hidden waterhole in that distant place. Now her memory of that life-saving oasis carries her family onward, her recollections spanning time to bring past and present together. In a cozy home at dusk, a faithful dog pads to the front door and waits, ears pricked and tail quietly thumping. Nearly every evening, around the same time, the dog grows expectant, wagging its tail before any footstep is heard. Somehow it knows the hour is near when its beloved human will return. Sure enough, minutes later, familiar footsteps approach and a key turns in the lock. The dog greets its owner with joyful barks, right on schedule. Even without a watch, it seems to feel the flow of the day, an inner sense of routine telling it that the long wait is over. In an oak woodland, a clever jay hops about, secretly burying acorns and seeds under the carpet of fallen leaves. The bird is caching food, not for now, but for a time it knows will come when the weather turns harsh and food is scarce. Days or weeks later, when the ground is frozen and bare, that same bird returns to unearth its hidden treasures. It remembers exactly where it hid each stash, scratching away snow and leaf litter to retrieve its meals. The jay even recalls which hiding spots hold food that spoils quickly and which contain longer-lasting nuts. It visits the perishable treats first, ensuring nothing rots away. With its tiny bird brain, it manages to recall not only the place of each cache, but a sense of how long ago it hid them. In the jay's actions, we see a shadow of planning for the future and recollection of the past, a primitive form of mental time travel. For many creatures, survival depends on these twin abilities to remember and to anticipate. In autumn woods, squirrels tirelessly gather acorns and bury them in dozens of spots. Then months later, sniff them out under winter's snow, guided by memory and keen scent. High above, flocks of migratory birds depart, just as the days shorten, leaving before winter arrives, timing their journey to when food will be plentiful at their destination. In the mountains, a bear eats ravenously as summer ends, instinctively fattening itself for the hibernation it somehow knows is coming with the cold. None of these animals consciously understands the concept of a season or tomorrow as we do. Yet their behavior shows a clear grasp of when to prepare, when to wait, and when to act. Their bodies and minds carry yesterday's lessons and respond to tomorrow's call without ever pondering the words for past or future. In the animal mind, time is a tapestry woven from experience and instinct. A hungry belly at dusk signals that night is approaching, just as a familiar chill in the air reminds a bird that winter will soon bite. But no animal marks the passing days on a calendar, or wonders what next year might bring. They live in time, but only as far as nature has equipped them, remembering what is needed from the past and anticipating what is imminent. The idea of measuring time, of slicing it into equal pieces and naming those pieces, lies beyond their grasp. That leap, from sensing time to defining it, was left to us. Humans, with our curious minds, would take the raw material of memory and anticipation and shape from it a concept of time stretching into past and future. And with that came the urge to track time's flow, to give it number and form, and hold on to the fleeting hours. In an ancient sun-baked city, a tall stone pillar casts a slender shadow that shifts as the day goes by. Long ago, people watched that shadow creep and realized it could divide the day into parts. In the morning, it stretched long to the west. By noon, it shrank to a stub beneath the pillar, and by evening, it extended far toward the east. By carving marks in the dirt where the shadow fell, they began to segment the day's progression. A simple stick in the ground became a tool to measure time. Thus was born the sundial, time told by the sun itself. As morning turned to midday and midday to dusk, the length and angle of the shadow told the story of each hour, allowing people for the first time to read the day's progress at a glance. When the sun went down, other ingenious devices took over to track the hours of darkness. In one land, a metal bowl with a small hole was set afloat in a basin of water. As water dripped through the hole at a steady trickle, the bowl would slowly sink at a predictable time. In this way, a simple water clock marked the watches of the night. In another place, people inscribed lines on a burning candle. As the wax melted down past each mark, an hour was said to pass. Across the world, different cultures found similar solutions. A glass vessel filled with sand let grains fall gradually to the lower half, an hourglass measuring an hour by the soft, ceaseless fall of sand. In distant temples, coils of incense burned with fragrant smoke. Carefully spaced knots in the coil would burn through at regular intervals, releasing a whiff of perfume or ringing tiny bells with each passing hour. By flame, by water, and by sand, humanity learned to count the time even in darkness, never again completely at the mercy of the night. As the centuries passed, the desire for more precise and automatic timekeepers grew. The flow of water and the burn of candles were useful, but they could only approximate the hours. In medieval Europe, the problem of timekeeping was taken up in the quiet sanctuaries of monasteries. Monks living by strict schedules needed to pray at set times, even in the dead of night when no sun or steady drip of water could be trusted to mark the hour. To meet this need, inventors in the 13th and 14th centuries devised intricate machines of wheels, gears, and weights, the first mechanical clocks. These early clocks had no faces or hands. Their sole task was to strike a bell at designated times. In a dim, pre-dawn hall, a bell might suddenly peal by itself, triggered by hidden levers and escapements like a mechanical rooster crowing on cue. The mechanical clock was born, a new heart that ticked by human design rather than by nature's rhythm. Only its ringing bell displayed the time. There was no dial or hand to see. Soon, these clocks ventured beyond monastery walls. In bustling town squares, tall clock towers rose toward the sky, housing great iron mechanisms powered by slowly falling weights. Each hour, a hammer inside the tower would strike a bronze bell, its deep tone ringing out over rooftops to announce the time. Villagers set their daily rhythms by those peals, opening the market at the 9 o'clock bell, pausing at midday when the bell boomed 12 times, and returning home as the evening bell tolled. To them, there was wonder in this new sound that governed the day. A machine was telling them the hour. The town clock became the communal heartbeat, coordinating the lives of bakers and blacksmiths, of children and elders, all by the steady ticking of an unseen engine. These first mechanical clocks were marvels of ingenuity, but they were far from perfect timekeepers. Their iron gears might stick, or their springs slacken, causing the clocks to run a little fast or slow. Every few days, a keeper had to climb the tower and adjust the machine by the sun, because noon on the clock's face would drift away from noon in the sky. Early clock dials, when eventually added, often had only an hour hand. Minutes and seconds were beyond the device's accuracy. Yet despite their flaws, the impact of these inventions was profound. For the first time, people had a man-made way to measure the passage of hours that was not tied directly to the heavens. The steady tick-tock of the clock began to regulate human life, adding a new layer of order atop the ancient rhythms of sun and moon. Humanity had, in effect, gained a new heartbeat to live by, in addition to the one we are born with. One evening, in a grand cathedral in Italy, a young scholar named Galileo Galilei stood transfixed by a lantern swinging gently overhead. As it swayed back and forth on its long chain, he noticed something remarkable. Whether the lamp swung in a wide arc or a small one, each swing took the same amount of time. He timed the swings against his own pulse, counting heartbeats for each full oscillation. The number of beats hardly changed as the lamp's arc grew smaller. In that moment, Galileo had discovered a hidden harmony. The pendulum's swing is isochronous, meaning each swing takes equal time. This revelation hinted at a new way to keep time with far greater accuracy than ever before. Not long after, inventors turned Galileo's discovery into reality. In 1656, the Dutch scientist Christian Huygens built the world's first pendulum clock. In this design, a pendulum swinging beneath the clock controlled the motion of its gears, acting like a steady heartbeat for the mechanism. The result was transformative, a timepiece that could keep time to within mere seconds a day, a level of precision unimaginable with earlier clocks. For the first time, clocks could reliably count off seconds as well as hours, and the familiar tick-tock of a swinging pendulum became the new sound of accurate time. The pendulum clock allowed people to schedule their lives to finer intervals and opened the door to timing scientific experiments and celestial events with new confidence. While pendulums brought accuracy, another innovation carried clocks out of towers and into people's pockets. As early as the 1500s, European clockmakers had learned to use coiled springs to power clocks instead of heavy hanging weights. This made it possible to create smaller, portable timepieces, pocket watches, and spring-driven clocks that one could carry from place to place. An early traveller might tuck a watch into his coat and listen to it tick softly by his side as he journeyed, a personal little clockwork heart accompanying him wherever he went. These early watches were often beautifully decorated and prized, though at first they were not very precise, sometimes gaining or losing an hour in a day. Still, they marked a turning point. Time became something an individual could possess and consult at will, not only hear from a town bell or see on a public dial. The tick of a watch hinted at a future when time would be ever more intimately woven into daily life. As timepieces grew more precise and portable, they soon faced one of history's greatest practical challenges: guiding ships across the open ocean. For centuries, navigators could determine their latitude, north-south position, by the sun or stars, but determining longitude, east-west position, proved maddeningly difficult. The key to longitude was time. If a sailor knew the exact time at a reference point, say, his home port, and compared it to local noon on his ship, gauged by the sun's height at midday, he could calculate how far east or west he had sailed. However, this meant carrying a clock on board that would keep the true time of the home port throughout long, turbulent voyages. In the 1700s, no clock could withstand the constant rocking of a ship, the varying humidity, and the temperature changes at sea without losing or gaining many minutes. Without a reliable timekeeper, ships often went disastrously off course. Indeed, shipwrecks from navigational errors were common. Solving this longitude problem became a desperate quest, and governments and scientific societies offered great rewards to anyone who could crack it. An unassuming English carpenter and self-taught clockmaker named John Harrison took up this challenge with fervour. Working far from any royal workshop, Harrison spent decades in the 18th century designing and refining special clocks for use at sea. He built his first sea clock, a massive, complex brass machine, then a second and a third, each time striving to overcome the issues that made other clocks fail on the waves. He tried novel solutions: wooden gears that wouldn't swell or shrink with humidity, new spring mechanisms to balance out a ship's rolling motion, and devices to compensate for temperature changes. Each new version of his sea clock improved in accuracy, but Harrison was a relentless perfectionist, never fully satisfied. He poured his life into the quest for a clock that would keep perfect time on a heaving ship, driven by the knowledge that such a device could save countless lives and revolutionize navigation. After many long years and multiple prototypes, Harrison finally created his masterpiece in the 1760s, a remarkably compact sea watch, much smaller and more practical than his earlier sea clocks. It looked like an oversized pocket watch, crafted with exquisite care. When tested on an ocean voyage, this chronometer performed beyond anyone's hopes. After a journey of thousands of miles, it was off by only a few seconds. Harrison had given the world a clock that could carry the true time from one shore to another, allowing navigators to pinpoint their longitude with unprecedented precision. At last, the oceans had signposts in time. A ship's position could be fixed by comparing local noon to the steady ticking of a reliable clock set to home port. The success of Harrison's chronometer ushered in an era of safer sea travel and opened the way for the global movements of people and trade with newfound confidence. It was a triumph of patience, ingenuity, and the human quest for accuracy. The triumph of the marine chronometer marked the dawn of a new age of precision. Through the late 18th and 19th centuries, clockmakers and scientists continued to refine timekeeping devices to ever higher standards. In royal observatories, astronomers timed the exact moments stars crossed the meridian, the imaginary line overhead, using pendulum clocks that could measure fractions of a second. In city centres, public clocks grew more accurate and more ubiquitous, and the idea of being on time became a new social expectation. As railways spread across continents in the 19th century, the need to coordinate train schedules led to the creation of standard time zones, regions where all clocks read the same time, synchronized by telegraph signals flashing across thousands of miles of wire. By the late 1800s, for the first time in history, clocks in distant cities struck the same hour together. The world was beating in unison to the rhythm of precise mechanical clocks. Life, commerce, and communication were now tightly bound to the clock's face, as humanity gained confidence that a minute would be the same minute everywhere, and an appointment at noon truly meant the same sun-crossing moment for all involved. And yet, keeping track of hours and seconds was only part of humanity's dance with time. Beyond the ticking of clocks lay the grander cycles of days, months, and years. People still looked to the sky to understand those broader rhythms. The spinning of Earth on its axis gave us day and night, but the journey of Earth around the sun brought the change of seasons, and the moon's waxing and waning marked the months. All these had to be tamed into a coherent system as well. To truly count every passing moment, from the beat of a second to the turn of a year, humankind turned its eyes to the heavens and created calendars, tying our human schedules to the vast cosmic clock that has been above us since the dawn of time. High in a northern sky, a group of ancient farmers gather to watch the sun set on the shortest day of the year. For weeks, they have seen the sun's arc sink lower and the daylight hours shrink. On this day, the winter solstice, the sun slips below the horizon at its southernmost point. They light fires and mark the spot, knowing that from tomorrow onward, the sun will begin to creep north again and the days will lengthen. Long before modern calendars, people learned to recognize such turning points in the year. By observing the heavens, they could predict the coming of cold and dark and the return of warmth and light, timing their planting and harvest to nature's cycles. Across the world, early cultures built structures to serve as giant calendars and celestial markers. In a green field in ancient Britain, massive stones were arranged in circles to align with the sun at key times of the year. At dawn on the summer solstice, the first rays of sunlight would pierce through a particular gap in the stones at Stonehenge, signalling the longest day of the year. In Egypt, great temples and pyramids were oriented with exquisite precision to the cardinal directions. Some temple sanctuaries were designed so that on one special dawn each year, the rising sun would illuminate a statue deep inside, marking an important anniversary. In Central America, Maya priests climbed pyramid steps to watch the equinox sun rise exactly due east, making sure their ceremonial calendar stayed on track. Everywhere, humans watched the sky and built lasting monuments to track the dance of the sun, moon, and stars, striving to bring cosmic order down to Earth. From these observations, the first calendars were born. Many early calendars were lunar, counting time by the cycle of the moon. People would watch the thin crescent of a new moon grow to a full moon and then wane to darkness, a cycle averaging about 29.5 days. 12 such moons made roughly 354 days, which fell short of a full solar year. As years passed, those who followed a strictly lunar count noticed their calendar drifting out of sync with the seasons, spring festivals creeping into winter's cold, harvest celebrations arriving when crops were still green. To correct this, some societies began adding extra days, or even an entire extra month now and then, to realign the calendar with the seasons. Other cultures turned directly to the sun to structure their year. The ancient Egyptians, for instance, were gifted observers of both sky and earth. Each year, they watched for the heliacal rising of Sirius, the brightest star, just before dawn. This event coincided with the annual flooding of the Nile River, which was critical for their agriculture. Noticing that roughly 365 days passed between each reappearance of Sirius and each Nile flood, the Egyptians devised a calendar of 365 days divided into 12 months of 30 days each, plus 5 extra days at the end. This calendar was an astonishingly practical tool. It allowed them to predict the Nile's inundation and plan their planting with confidence. By anchoring their year to a star and the sun's cycle, they aligned their civil life with the cosmic rhythms overhead. As civilizations grew and records stretched across generations, the accuracy of calendars became ever more important. By the time of the Romans, it was clear that a 365-day year was slightly too short. The true solar year is about 365.24 days. The early Roman calendar, originally lunar, had grown chaotic over time until Julius Caesar reformed it in 46 BCE with the help of Greek astronomers. Caesar's new Julian calendar mandated a 365-day year, with an extra day added every fourth year, February 29th, to account for that quarter-day fraction. This leap year system kept the calendar roughly on track for many centuries. With the Julian calendar in place, the dates of festivals and the timing of seasons remained more consistent year to year, a great relief to administrators and farmers who could trust that, say, the spring equinox would fall around the same date each calendar year. However, even the Julian calendar wasn't perfectly precise. Over the centuries, its slight error, about 11 extra minutes per year, accumulated. By the 1500s, the calendar had drifted 10 days off. The spring equinox, which had once fallen on March 21st, was now occurring on March 11th, according to the calendar. To fix this, Pope Gregory XIII introduced a refined calendar in 1582. 10 days were simply dropped from that year to bring the date back into alignment with the season. In the Papal States and several Catholic countries, people went to sleep on the night of October 4th, 1582, and awakened the next morning on October 5th, 1582-15. Additionally, new rules were set. Century years would not be leap years unless divisible by 400,
thus 1600 was a leap year, but 1700 was not, for example, preventing the calendar from drifting again. This Gregorian calendar reform was gradually adopted worldwide over the next few centuries and remains the international standard today, keeping our dates and seasons tightly in step with the Earth's journey around the Sun.
With the calendar, humanity bound itself to the cosmos. We learned to name each day, count each year, and predict the seasons by studying the sky. Today, the Gregorian calendar, with its leap years, keeps the world synchronized with Earth's orbit. And while many cultures still cherish their own traditional lunar or solar calendars for holy days and New Year's, the essential challenge has been met. We have mapped the grand cycles of the heavens onto our lives. We have, in a sense, taught ourselves to step in time with the universe. Yet for all these achievements, time itself remains an ever-deepening mystery. The more precisely we measure it, the more it seems to challenge our understanding. But that is a tale for another time, as our journey through the story of time continues onward, ever into tomorrow. Imagine holding a clock in your hand, while another clock speeds away on a fast-moving train. Common sense says both should tick the seconds in unison, each moment matching perfectly. Yet as the train approaches incredible speeds, something astonishing happens. The moving clock's ticks begin to slow compared to the clock resting in your hand. This is not a trick of perspective or a mechanical glitch. It is a fundamental truth of nature discovered in the early 20th century, one that forever changed how we understand time itself. Before Einstein's revelations, the idea of time was simpler and seemingly obvious. Sir Isaac Newton and those after him treated time as a universal, absolute flow, a single giant clock ticking the same for everyone throughout the universe. According to that classical view, seconds marched forward uniformly, never altering their rhythm regardless of how one moved or where one was. This comforting certainty prevailed for centuries. But as the 20th century dawned, cracks began to appear in this notion. It would take Einstein's leap of imagination to show that time is not the rigid backdrop Newton imagined, but a flexible dimension intertwined with space. In our everyday lives, time feels absolute, flowing evenly for everyone, everywhere. But a young Albert Einstein began to question this comfortable notion by asking simple yet profound questions about light and motion. He imagined what it would be like to chase a beam of light through space and wondered what strange things might happen to time along the way. In exploring these questions, Einstein uncovered an extraordinary insight. Time can stretch and shrink depending on how you move. The faster you travel, especially as you approach the cosmic speed limit of light, the more time itself relaxes its pace for you. Einstein's breakthrough sprang from a simple but profound principle. The speed of light is the same for everyone, no matter how fast they are moving. This seemingly innocent fact hides a universe-altering implication. If nothing can outrun light, then the laws of nature must somehow adjust to prevent any chase from succeeding. So, as you accelerate toward light speed, the universe subtly changes the rules. Time itself slows down for you, and even space distances compress, all to ensure that light's lead remains unbroken. In this way, the cosmos maintains its ultimate speed limit while gently altering your own passage through time. For the first time, time itself was revealed, not as a separate stage on which events simply unfold, but as something intertwined with space. Einstein's theory introduced a new tapestry called spacetime, a four-dimensional fabric weaving together space and time into one. In this unified picture, motion through space affects motion through time, and vice versa. One way to imagine it is to picture each of us always moving through space-time at a fixed cosmic speed. If we remain still in space, all of our motion carries us forward through time. As we rush faster and faster through space, we divert some of that motion away from time's flow, and so we experience time more slowly. It is as if there is a cosmic speed budget that must be shared between movement through space and progress through time. For the universe to keep its balance, time adjusts as part of this dance of motion. This elegant interplay means that time is not a universal metronome ticking independently of the world, but part of the choreography of the cosmos itself. Consider a long journey at near light speed. For an astronaut racing through space at unbelievable velocity, the seconds aboard their ship pass slowly and sparingly. Back home on Earth, those same seconds accumulate more quickly. The traveller might find that only a few years have elapsed during the voyage, while decades have gone by for those who stayed behind. This scenario, often told as the tale of twins, where one ventures into space and returns younger than their sibling, isn't science fiction. It is a real consequence of nature's design, a vivid illustration of time's flexibility. Such time-bending effects are not just thought experiments. They have been measured in the real world. Scientists synchronized precise atomic clocks, then sent one flying around the globe on a jet plane while the other stayed on the ground. When reunited, the travelling clock was found to be ever so slightly behind its stay-at-home twin. Its time had literally lagged, proving that moving through space had altered its passage through time exactly as predicted. Even subatomic particles provide evidence. Unstable muons created high in Earth's atmosphere live longer when they hurtle toward the ground at high speed than they would if standing still. In the strange reality of relativity, moving swiftly becomes a ticket to a slower journey through time. Einstein also realized that even the notion of simultaneity, whether two events happen at the same time, depends on the observer. Imagine a long train moving past a platform. Two bolts of lightning strike the front and back of the train. An observer standing on the platform sees the flashes at the same moment and concludes they occurred simultaneously. But an observer riding in the middle of the moving train, travelling toward one flash and away from the other, sees the front flash first and the rear flash a moment later. To the train passenger, the two lightning strikes were not simultaneous. Neither observer is wrong. Rather, each has their own valid timeline. This thought experiment revealed that time and sequence can differ from one vantage point to another, a shocking departure from the old idea of universal time. In this new understanding, there is no single master clock ticking the true time for everyone. Instead, each observer carries their own clock, and those clocks can disagree depending on their motion relative to one another. One person's now can be another person's earlier or later. An event that one observer marks at a certain time might be recorded at a different time by another who is moving differently. Time, once thought to be absolute, became a personal experience, variable and woven into each observer's perspective. Despite its mind-bending nature, relativity's effect on time has little impact on our daily routine. At the speeds we move, cars, airplanes, even fast jets, the time slowing is so tiny that it passes unnoticed. The difference amounts to mere billionths of a second, far beyond the perception of our senses. Only when we travel at a significant fraction of light speed do these effects become dramatic. It is as if time keeps its secrets hidden until we push it to its extreme limits. Yet simply knowing that time can bend and diverge changes how we see reality. The ticking of a second is not guaranteed to be the same for all. It depends on the path we take through the cosmos. This invites a sense of wonder and humility. Two friends can part ways and later reunite, only to find one has aged less than the other. Time emerges not as a rigid backdrop, but as part of the living, dynamic tapestry of the universe. It suggests that each life, each journey, carries its own clock, personal and unique, tied to that journey's twists and turns. This revelation was only the beginning. If motion through space can slow the passage of time, might there be other ways nature can alter the clock's beat? One of Einstein's further insights hinted at the answer, and soon it would become clear. The next clue comes from an even more pervasive feature of our universe, one that envelops us constantly, yet we barely notice its effect on time's flow. Gravity, the gentle pull binding together stars, planets, and ourselves, also has a say in how time passes. High on a mountaintop, time flows ever so slightly faster than it does down in the valley below. This sounds like fantasy, but it is a measurable reality. Gravity, the very force that holds us to the earth, can stretch and squeeze the flow of time. Up on the mountain, farther from Earth's gravitational pull, each second passes just a tiny bit quicker. Deep in the valley, or at sea level, where gravity's grip is stronger, time inch by inch runs a little slower. The difference is too small for us to feel, yet it is there, quietly revealed by the most sensitive clocks. Einstein had anticipated this strange effect, as he extended his theory of relativity to include gravity. He realized that a gravitational field could be seen as bending not just space, but time as well. The stronger the gravity, the more steeply time's river slows in its descent. A clock closer to a massive object will tick at a lazier pace compared to one farther away. Time itself, Einstein found, is part of the texture of the gravitational field. Where gravity intensifies, time dilates and relaxes its pace. Modern experiments have confirmed this truth beyond any doubt. Scientists have compared ultra-precise atomic clocks at different heights. For example, one clock at the base of a tall building and another at the top. Sure enough, the clock lower down, deeper in Earth's gravity well, ticks just a hair more slowly than the one above. Even a difference of a few floors or a small hill is enough for sensitive instruments to detect that time is passing at slightly different rates. In fact, the latest generation of optical atomic clocks is so sensitive that moving one clock only a foot higher than another will make it tick a bit faster, a difference we can now measure. Our everyday world doesn't reveal this directly, but our technology does. The satellites that enable GPS navigation carry clocks that tick faster in orbit than they would on the ground. High above Earth, freed from some of our planet's gravity, those satellite clocks gain a few dozen microseconds, millionths of a second, each day. Engineers must correct for that tiny gain, otherwise our maps and phone directions would slowly drift off course. Remarkably, every time you use GPS to find your way, you are witnessing Einstein's gravity-time relationship in action, ensuring that your position on Earth is computed correctly. If gravity can tweak time on Earth by subtle amounts, its effects in more extreme settings are positively mind-bending. Imagine a traveler venturing near an enormously massive object like a neutron star or a black hole. To the traveler, time feels normal. Their heart still beats second by second. Their thoughts flow as usual. But an observer watching from a safe distance would see something very different. As the traveler drifts closer to the massive object, each second for them appears to stretch out. Their movements slow, their clock ticks languidly, as if some unseen hand were pressing a cosmic slow-motion button. The closer our intrepid traveler gets to the black hole, the more pronounced this effect becomes. From afar, you might see them drift toward the dark boundary, the event horizon, yet never quite cross it. Each moment appears more and more drawn out. In fact, at the very edge of the black hole's grip, time for the traveller would seem to nearly stop relative to the outside universe. They could wave a hand or call out, but to you that wave might take eons, and the call might never reach your ears. In reality, the traveller slips through the threshold in their own experience, yet to the rest of the universe they remain suspended, frozen at the brink. Time, in the strongest embrace of gravity, becomes almost unrecognizable. Black holes represent an extreme, but they highlight a universal truth. Gravity and time are intimately linked. Every massive body, our Earth, the Sun, or the center of our galaxy, creates its own leisurely distortion of time. We live our lives submerged in the gentle slowing caused by Earth's mass, aging a tiny bit less quickly than we would in the emptiness of space. If you could live your entire life atop a high mountain, you would be ever so slightly older at the end than if you had lived at sea level, all thanks to the weaker pull of gravity above. These differences are minute in everyday terms, but they remind us that time is not absolute. It flows differently in different places, depending on the mass that envelops those places. This realization deepens the wonder introduced by relativity. Time is malleable, not only due to motion, but due to gravity's presence. Yet, whether stretched or squeezed, time still moves ever forward, never backward. No matter how high a mountain we climb, or how fast a spaceship we ride, we cannot reverse the direction of our days. There is an underlying order to time's passage, a built-in arrow pointing from yesterday to tomorrow. To understand why time has a direction at all, we must step away from relativity and gravity and look at something even more fundamental: the rise of disorder and the arrow of time. A delicate porcelain cup teeters on the edge of a table, falls, and shatters into pieces across the floor. No matter how long you wait, those shards will not leap back together to form the cup again. A drop of ink spreads in water, and you will never see the swirls gather back into a tidy drop. In our everyday experience, some processes seem to move irreversibly in one direction. We sense that time itself has a preferred way of unfolding, an arrow pointing from what we call the past toward what we call the future. This one-way direction of time is commonly known as the arrow of time. But what gives the arrow its direction? The answer, as physicists have come to understand it, lies in a concept called entropy, a measure of disorder or randomness. When the cup was intact, its molecules were arranged in a very organized way. Once broken, that order is lost. The pieces and splinters on the floor represent a state of much higher disorder. In nature, it turns out that it's vastly more likely to go from order to disorder than the other way around. Entropy tends to increase with time, and in doing so, it marks time's forward march. Imagine filming the shattering cup and then playing the movie in reverse. In the backward version, shards miraculously jump up and reassemble into a cup. It looks absurd because it never happens in reality. Not because it's absolutely impossible by the basic laws of physics, but because it's overwhelmingly improbable. The fundamental laws that govern the motion of individual atoms and molecules are mostly reversible. They don't care about past or future. Yet when enormous numbers of particles come together, the chances of all their tiny motions lining up just right to rebuild a broken cup are astronomically small. Nature doesn't outright forbid such a reversal of entropy. It's just that the universe would have to get unimaginably lucky for it to occur. Thus, we effectively never see broken things unbreak or cold things spontaneously warm up. The arrow of time is essentially an arrow of increasing entropy. It dominates our macroscopic world. We witness this arrow everywhere. A hot cup of tea left on the counter will cool down as heat dissipates into the air. Never will it spontaneously become hotter by drawing heat from a cooler room. Buildings crumble over centuries. We never see ruins spontaneously assemble into new structures. Our bodies age with time, cells accumulating damage and disorder, and we cannot unage to grow younger. All these changes reflect entropy increasing, energy spreading out, structures breaking down, arrangements becoming more disordered. The forward direction in time is the direction in which overall disorder grows. Why was yesterday more ordered than today, and why will tomorrow likely be more disordered still? The answer may lie at the very beginning of time as we know it. Physicists believe that our universe started in an extremely ordered state, a state of very low entropy, at the moment of the Big Bang. Over billions of years, as stars have burned their fuel and galaxies have formed and evolved, entropy has been rising. Each moment inherits the growing disorder from the last. In a sense, the arrow of time is set by this ongoing increase of entropy that began eons ago. Time's one-way flow is, at its core, a journey from the pristine simplicity of the early cosmos to the complex, scattered reality we see now and into the future. If entropy keeps increasing, one can imagine a time in the far future when it approaches a maximum, when all order has dissolved. In theory, there may come an era, billions upon billions of years from now, when the stars have burnt out, black holes have evaporated, and matter itself is spread thin and uniform. No useful energy remains anywhere to fuel change. The universe would reach a state called heat death. In that final stillness, the arrow of time would lose its meaning, for with nothing changing, there is no way to distinguish one moment from the next. That ultimate equilibrium is an unfathomably distant possibility. Now we live in a vibrant universe, still far from such homogeneity, where time's arrow continues to drive stars to shine, planets to form, and life to dream about tomorrow. This thermodynamic arrow of time has profound implications for how we experience life and memory. We remember the past, but not the future, because memory formation is an irreversible process. It imprints a lasting change, an increase in entropy, on our brains. You can recall dropping that cup because the event left a physical trace in your mind, but there is no analogous record from the future. Cause precedes effect. We can influence what happens next, but we cannot reach back to change what has already occurred. These truths align with one simple rule. In a closed system, entropy will not spontaneously decrease. The past is fixed in records and memories, while the future remains unformed and full of possibilities, yet inevitably bound to unfold along the path of increasing disorder. The arrow of time gives our universe a narrative, a past to remember, a present to experience, and a future to anticipate. It is why we feel nostalgia for what was, and curiosity for what will be. Yet deep in the laws of physics, there is a puzzle. The equations that describe fundamental particles work almost the same, whether time runs forward or backward. How, then, does the unmistakable arrow emerge? The prevailing view is that it comes from those special initial conditions of the universe and the overwhelming tendency toward entropy growth thereafter. Still, the arrow of time leaves us with a sense of mystery. Time carries a direction that none of us can reverse, tied intimately to the fabric of the cosmos and the unfolding story of everything in it. Even as we accept that time's arrow points forward, we are left with deeper questions. Is the arrow of time an absolute, fundamental part of reality? Or could it be a byproduct of something else? Perhaps the universe's initial conditions. Could there be pockets of the cosmos where entropy decreases and time runs backward? Or is that pure fantasy? These musings remind us that time holds secrets yet to be unraveled. To probe further, we turn to the world of the very small, where the rigid rules of classical physics give way to the strange dance of quantum mechanics. In that realm, the flow of time takes on a new character, one governed by uncertainty, fluctuations, and probabilities, as if the ticking of the clock at the quantum scale is whispered rather than struck loudly. In the subatomic realm, the precision and certainty we take for granted in daily timekeeping begin to blur. At this scale, events do not follow a strict clockwork schedule, but unfold with an inherent unpredictability. A radioactive atom, for example, might decay and release its energy after a minute, or it might hold on for a day or a year, and there is no way to know exactly when. We can predict its average lifetime, but not the precise moment of its decay. In quantum physics, time becomes a game of probabilities, where the when of a happening is often smeared out like a diffuse cloud rather than a pinpoint. This unpredictability is woven into the fabric of quantum theory. There is a fundamental limit to how precisely certain pairs of properties can be known, and one such pair is energy and time. If you try to measure a process that happens in a vanishingly short time, the energy involved in that brief moment becomes uncertain. It is as if nature allows a little fuzziness. A particle can borrow energy for a tiny moment, as long as it pays it back quickly. This is the essence of the energy-time uncertainty principle. As a result, what we think of as empty space is not truly empty at all. It seethes with spontaneous flickers, known as quantum fluctuations, where particles and antiparticles briefly appear and vanish before anyone can definitively say they existed. These phantom particles popping in and out of existence might last only a trillionth of a second, or even less, but collectively, their presence can be felt. They contribute a jitter to the otherwise smooth background of reality, a gentle quantum noise permeating space and time. At the tiniest scales, near what physicists call the Planck time, around 10 to the minus 43 of a second, time itself may lose its usual meaning. In that extreme realm, the distinction between one moment and the next blurs, and the smooth river of time may break into a froth of quantum foam. We cannot measure such tiny intervals with any current technology, but our theories suggest that at the Planck scale, the calm flow of time we experience gives way to something far more chaotic and uncertain. All of this suggests that time, at heart, might not be as continuous or as fundamental as we perceive it to be. Some thinkers have even proposed that time could be an emergent property, not a basic ingredient of the universe, but a byproduct of something deeper, like the entanglement of quantum states. While these ideas remain speculative, they underline how mysterious time becomes when examined through the lens of quantum mechanics. In the equations of quantum theory, time is often treated as a simple background parameter, ticking away steadily in the distance. But we know from Einstein that time can bend and flex, and marrying these two views, the quantum and the relativistic, is one of the great challenges of modern physics. Even cause and effect take on a strange character in the quantum world. In certain experiments, the sequence of events can become ambiguous, as if nature itself has not decided an order until we observe it. Particles can influence each other instantaneously across vast distances through quantum entanglement, a phenomenon that Einstein famously dubbed spooky action at a distance. This does not allow us to send messages back in time or violate causality, but it hints that our intuitive sense of time and separation is incomplete. Furthermore, a particle in quantum mechanics does not even trace a single, definite history as a classical object would. Instead, it can exist in a blend of multiple states or paths at once, a phenomenon known as superposition, until something forces a choice. In practical terms, an electron can seem to take many routes simultaneously or occupy several energy states at the same time. Only when an observation is made does this cloud of possibilities collapse into one concrete outcome. This means that the story of what happened and when, at the quantum scale, can remain undecided, almost as if time itself waits for a measurement to pin down the sequence of events. Yet, amid this uncertainty, quantum mechanics also provides the tools for some of the most precise timekeeping imaginable. Ironically, the same quantum leaps and vibrations that seem so unpredictable on one level can be harnessed in large numbers to keep incredibly steady time. The oscillations of atoms, the tiny jiggling of electrons moving between energy levels, turn out to be among the universe's most reliable metronomes when viewed in aggregate. By counting these oscillations, we have built atomic clocks that divide time into astonishingly fine slices, far smaller than anything our senses can directly perceive. These clocks are so precise that they would only err by a second over the span of millions, even billions, of years. The marriage of quantum phenomena with time measurement marks a triumph of human ingenuity. It's a beautiful twist. The very theory that introduces fundamental uncertainty has enabled us to measure time with unparalleled accuracy. But how exactly do these atomic clocks work? And what makes them so precise? To answer that, we journey from the world of theory into the laboratory, into the ticking heart of the atoms themselves, to see how we measure the unmeasurable with such confidence and exactitude. Humanity's quest to measure time has evolved from sundials and hourglasses to pendulum clocks and quartz watches. But the most profound leap came in the mid-20th century, when scientists turned to the atoms themselves to mark the passage of seconds. For millennia, we based our timekeeping on the rotation of the Earth and the swinging of mechanical pendulums, rhythms set by nature and refined by engineering. Those methods, while revolutionary in their day, had limitations in precision. The Earth's rotation, for instance, gradually slows and wobbles, and even the best pendulums are affected by temperature and local gravity. To truly transcend these limitations, timekeepers needed a more fundamental, unwavering tick, and they found it in the oscillations of atoms. In 1967, the world officially redefined the second, not by the motion of heavenly bodies, but by the behavior of cesium atoms. An atomic clock uses the natural vibration of cesium, and nowadays other elements like rubidium or strontium, as its pendulum. Inside an atomic clock, a cloud of cesium atoms is carefully manipulated by magnetic fields and lasers. The atoms are made to absorb and emit energy at a very specific frequency, flipping between two energy states. That frequency turns out to be extraordinarily stable. 9,192,631,770 cycles of the corresponding microwaves occur in 1 second. In simpler terms, over 9 billion tiny swings of a cesium atom's pendulum make up 1 second. This definition is so exact that anyone, anywhere with the proper equipment, can reproduce the same second using the same atomic reference. It provided a universal time standard far more stable than the spinning of the Earth or the ticking of any mechanical clock. The design of atomic clocks is a marvel of precision engineering. Imagine the cesium atom as a tiny clock face and its oscillation as the ticking hand. In a typical cesium clock, atoms are funneled into a vacuum chamber and hit with microwave radiation. If the microwave frequency is tuned just right, matching the atom's natural vibration, the cesium atoms will undergo a kind of resonance, like pushing a swing at exactly the right rhythm. The clock detects this resonance by checking how many atoms change their energy state. It then locks the microwave generator to that exact frequency, which maximizes the atom's response. Once locked, The steady oscillations of this frequency are counted and become the clock's time signal. The result is a timepiece of astonishing steadiness, largely unaffected by external fluctuations, a clock keeping time with the heartbeat of an atom. Such a clock can run for years without missing a beat or needing adjustment. The precision achieved by these devices is almost unimaginable. A good cesium atomic clock will not gain or lose a single second in tens of millions of years. And newer clocks, using atoms like strontium and the higher frequencies of visible light, so-called optical clocks, push the boundaries even further. Their accuracy is such that they would deviate by only a second over the entire age of the universe. With such clocks, scientists can detect minute differences in the passage of time between locations just a few centimeters apart in height, echoing Einstein's predictions that we saw earlier. Timekeeping has reached a realm where simply moving a clock to the top of a bookshelf makes a measurable difference. It is likely that in the near future, the official length of a second will be redefined using one of these optical clocks, as they have become even more stable than the cesium standard. This extreme precision isn't just for bragging rights. It underpins much of our modern world. The Global Positioning System, GPS, for example, relies on atomic clocks aboard satellites to triangulate positions on Earth. Each GPS satellite carries multiple atomic clocks broadcasting time signals, and the exactness of those signals allows receivers to calculate distance and location to within meters. If a satellite's clock were off by even a single microsecond, a GPS map could be wrong by hundreds of meters. That is why engineers correct the satellite clocks for Einstein's effects, both the time slowing from their high speed and the time fastening from being high above Earth's gravity. These adjustments ensure that, despite hurtling through space, the satellite clocks stay synchronized with clocks on the ground. In essence, without such relativistic corrections, the GPS network would quickly drift and lose accuracy. Every time we get directions on a smartphone or make an electronic bank transfer, we are relying on the ultra-precise beats of atomic clocks far above us. Beyond everyday technology, atomic clocks have become essential tools in science. They allow tests of fundamental physics, for instance, checking whether the constants of nature are truly constant or if they change ever so slightly over years. Arrays of atomic clocks spread across the globe can be used together to detect faint gravitational waves rippling through Earth by noticing tiny changes in the synchronization of the clocks. Astronomers and physicists also use atomic time to precisely track spacecraft and to measure the motions of celestial objects. In these ways, the atomic clock is not just a timekeeper, but a measuring stick for the fabric of spacetime itself, sensitive to subtle shifts and twists predicted by theory. Today, dozens of atomic clocks in laboratories around the world are compared and averaged to create international atomic time, the official collective heartbeat of our civilization's clocks. The advent of atomic time has even forced us to tweak our civil timekeeping. Because atomic clocks are so steady compared to Earth's rotation, noon as defined by the sun will slowly drift relative to noon by atomic clock. To keep the two aligned, timekeepers occasionally add a leap second to our civil time, essentially pausing the atomic count for 1 second to let Earth's rotation catch up. This adjustment, made every few years as needed, is a reminder that our planet's natural rhythms are not as uniform as the beat of an atom. We have, in a sense, surpassed Mother Nature's timekeeping and established a new standard that outperforms the turning of the heavens. Holding an atomic clock to your ear, you would hear nothing of its rapid ticking, yet its impact reverberates through our lives. The ability to measure time so finely is a triumph of human ingenuity. We have managed to take something as evanescent as the passing moment and pin it down with incredible exactness. As we consider time on Earth with these marvels of precision, it's worth remembering that the universe has been keeping its own time long before we built our clocks. Out in the cosmos, celestial objects pulse, spin, and cycle with regularity, serving as natural clocks on grand scales. We now turn to these cosmic timekeepers, from rapidly spinning neutron stars to distant quasars, to see how the universe itself marks the passage of ages. High above, in the deep vacuum of space, nature has been keeping time long before humans built their first clocks. One of the most remarkable cosmic timekeepers is the pulsar, a type of neutron star left behind after a massive star explodes. Pulsars are incredibly dense, city-sized spheres that spin at dizzying rates, flashing beams of radiation from their magnetic poles like cosmic lighthouses. With each rotation, a pulsar sends a pulse of light or radio waves toward Earth. Some spin hundreds of times each second, and their pulses arrive with such regularity that they rival the precision of atomic clocks. In fact, when the first pulsar was discovered in 1967, its radio blips were so evenly spaced that the astronomers jokingly nicknamed it LGM1 for Little Green Men, half in jest at the idea it might be a signal from an intelligent civilization. Of course, it turned out not to be aliens at all, but a natural beacon, a star ticking away the moments with uncanny steadiness. This whimsical episode illustrated how astonishingly clock-like these stellar remnants truly are. It marked the beginning of a new way to tell time on a cosmic scale, using the rotations of collapsed stars as the universe's own timepieces. Pulsars have since become vital tools for astronomers, measuring time and testing physics under extreme conditions. By monitoring the timing of pulsar flashes, scientists can detect subtle effects, like the slight wobble induced by an orbiting companion, or even the ripple of distant gravitational waves stretching and squeezing spacetime. A network of millisecond pulsars scattered across our galaxy now serves as a gigantic gravitational wave detector. Tiny irregularities in their otherwise clock-like beats could reveal the passage of those faint cosmic tremors. Such applications show that pulsars are not only cosmic clocks, but also cosmic laboratories, their consistent ticking enabling us to probe the universe's deepest phenomena. In the future, these cosmic lighthouses might even guide interstellar travelers, serving as a kind of galactic GPS, their steady beats allowing spacecraft to navigate by the stars. Quasars, another class of celestial timekeeper, operate on a different scale. A quasar is the brilliant core of a young galaxy, powered by a supermassive black hole devouring matter and unleashing torrents of energy. Quasars don't blink with a neat rhythm like pulsars. In fact, their light can flicker and flare in complex, irregular ways, but they serve as signposts of time in a more profound sense. The light we see from a distant quasar began its journey billions of years ago, long before the Earth even formed. When we observe a quasar through our telescopes, we are literally gazing backward in time. It's as though the universe's past is written in that far-travelling light, finally reaching us after crossing immense gulfs of space and epochs of history. In this way, quasars act like time capsules. By studying them, we glean clues about the early cosmos and trace how cosmic time has unfolded over eons. Even on the grandest scale, the universe itself provides a sort of clock. The expansion of the universe, the steady stretching of space since the Big Bang, can be thought of as a ticking hand of cosmic time. Distant galaxies recede from us, and their light is shifted to longer, redder wavelengths the farther away they are, as a result of this expansion. By measuring these shifts, the redshifts, we effectively read the universe's clock and can tell how long the light has been in transit. From such observations, we've determined that our universe has been expanding for roughly 13.8 billion years. In other words, by using the cosmos as a clock, we estimate the time elapsed since the universe's fiery birth. Effectively, the age of the universe itself. For instance, the cosmic microwave background radiation is the faint afterglow from a time about 380,000 years after the Big Bang, essentially a snapshot of the universe's early moments of light, which we use as a fixed reference point in cosmic history. From the ultra-fast blinking of a millisecond pulsar to the slow drift of galaxies over eons, the universe spans a breathtaking range of tempos. Each cosmic timekeeper, whether a spinning neutron star, a variable quasar, or the very expansion of space, adds a chapter to the story of time. Together, they remind us that time is woven into the fabric of the cosmos at every scale. Our own endeavours, like atomic clocks and space observatories, are our way of tuning into these natural rhythms, syncing our human sense of time with the grand orchestra of the universe. As we consider all these clocks, human-made and cosmic, we come full circle to the fundamental mystery of time. We can measure intervals down to astonishing fractions of a second and watch ages unfold across billions of years. Yet there is still something elusive about time itself. It's the medium in which all events happen, a flowing river that we ride every moment. It is also a dimension we have learned to shape and quantify through science. But why does time exist at all? And why does it seem to move ever forward, never backward? Such questions still puzzle philosophers and physicists alike. In our journey so far, we have seen how the universe learned to count its seconds and how we joined that cosmic chorus with our own precise clocks. Yet the deeper nature of time remains an open question, an unsolved riddle that beckons us onward. Our exploration is not over. There are more wonders of time left to ponder.